to introduce Coral Guiglio from TrustMe, and he will talk about the development of superheated water vapor propulsion system at TrustMe. So please, Julio.
Thank you. So yes, hello everyone, and thanks for the introduction. 1 second that I share my screen. Okay, everything should be working. Okay, yes, I'm Giulio Coral, and as mentioned, today I'm going to speak about the development of superheated water vapor propulsion systems at TrustMe. You probably heard about TrustMe, but in case you haven't, so we are a company founded in 2017, leveraging knowledge and research from our founders at CNRS and École Polytechnique for about a decade. We've been founded about 3.5 years ago to commercialize and develop these technologies into viable products. We are a team of about 20 between engineers, scientists, some of which with PhDs, which have fairly heterogeneous competencies in different scientific fields. We have pretty good knowledge and know-how about iodine propulsion, as far as we understand. And as such, we've been so far the only company which has been able to demonstrate iodine propulsion systems in space. So yes, you probably heard about us using iodine. Why we like iodine so much? Iodine is solid at room temperature, so it gives makes a lot easier the whole storage and delivery process. You don't need to pressurize, which also simplifies the launch. You can deliver the thruster system pre-filled to the client without practically any restriction. You can apply commercial. From a propulsion point of view, it is very similar to xenon for the use of using electrostatic or electromagnetic thrusters. So you have heavy atoms, 253U. It's very dense, so you can store a lot, and it has a low ionization energy. From a budget point of view, it's another aspect that many of the current xenon users are considering. So xenon is scarce and very expensive. We are talking in the $2,000 per kilogram. Iodine is in the order of 1/40th of the price of xenon. So yeah, on the spot market, you can literally buy iodine for tens of dollars per kilogram. So a lot of benefits, which is why in general we've been using iodine so far. Thrusters that we've been deploying. So the first one was the I-2T5. The I-2T5 is a cold gas iodine thrusters, and it's the first iodine thruster with flight heritage. So the first one we've been flying. So the I-2T5 is a very simple solution. It has a tank in which iodine is stored. It's sublimated and it's ejected through a conversion divergent nozzle to produce the same effect as a cold gas thruster, but without any pressurization. Now, you can see the performance on the bottom left. So it has a total impulse of 75 Newton second. The form factor is very compact, it's alpha U. So it's generally indicated for satellites of the scale of nanosats as a low-cost solution to improve lifetime. You can see on the bottom right the difference between just leaving the satellite fall by itself and having a little bit of thrust from the I-2T5. It extends the lifetime by several months. Now, the product we are probably most famous for is the MPT30, specifically in the I2 version. So this is an integrated gridded ion thruster system, which means that, yes, you have the ion thruster, the storage tank, all the electronics in 1U or 1.5U. You just send the command to the thruster and it's now thrust. So this is as well the first electric propulsion system using iodine ever demonstrated. We've been flying a couple of them so far. here, the performance, you can see we are on a totally different scale, like several thousands of Newton seconds. Depending on the version, it can be more or less based on the tank. This one offers especially, Jesus Christ, give me a second, I have the, there is some sort of automatic play. Okay, I'm gonna try to fight the automatic play myself. 1 second, presenter view. I'm sorry. I'm gonna try to have it to hold it fine. Okay. So very high total impulse in a relatively compact format, which means even in a small volume you can deliver substantial performance. The performance curve is shown on the bottom right, so you can have different power levels, different combinations of thrust and total impulse. This is one picture of the MPT-30 operating on iodine. You may have seen very often the beam of xenon. Iodine is a bit different. So you have this yellow-colored ion beam that leaves the thruster. So yeah, the products we have flight proven so far are the HUT5 and the MPT-30 series. You've probably seen in previous presentation about the clustering of MPT-30, which basically delivers higher thrust and total impulse for somewhat larger satellites. Yeah, this one as well, ready and coming soon. A bit further down the future, the MPT-300 series for small and medium satellites. So what I'm going to be talking about today is a new series of propulsion systems for advanced maneuvering capabilities, and yeah, can be used for a different series of maneuvers. Now, as the title suggested, we are going to be using water in this new project. So here is a bit of a comparison on why we like both iodine and water, although of course for different purposes. Both of them can be stored unpressurized, so iodine solid and water as liquid. Both have high storage densities and can be delivered pre-filled to the customers. But iodine is very heavy. It's a very heavy atom. So it's great for electrostatic and electromagnetic thrusters. Water is a relatively light molecule, so it's great for electrothermal thrusters. It's basically the way you accelerate it. You're probably familiar how it works. A lighter molecule delivers better performance for electrothermal thrusters. Better than this, there's of course hydrogen, but it has storage issues, let's say. Now, how we go from a cold gas thruster to a hot steam thruster. Cold gas thruster is literally the most simple propulsion system one can imagine. You have a storage tank in which you normally have a pressurized gas and a thruster. You want to increase a bit the ASP, you add a resistor at the thruster, and then let's say you want to prevent freezing trouble, you put a heater on the tank. Now, some people have tried to do this. It's been both at Surrey and at NASA. What happens if you just have a tank in which water is stored and thruster and gets out of a thruster? You get droplets. So the thruster starts not only spraying water vapor, but also droplets. This reduces the ASP, plus droplets freeze because they go through a convergent-divergent nozzle, and yeah, by decreasing their temperature to increase the velocity, yeah, they freeze and they form these ice cones. This caused several severe trouble, both for this Surrey mission and for the NASA one, in which they found, yeah, either they preload a lot less water, or they're gonna have freezing, so lose a lot of the propellant without generating, of course, any thrust. Now, Okay, we need to do a bit of a modification to this because, yeah, we've seen that approach doesn't work. So we add a separate storage tank in which we store water in a bladder, and then we inject a little bit of water in the vaporization tank. The water here is then vaporized, and then it's further heated in the thruster. Now, the question is, how much should we heat up the water in the thruster? I added on the top right, you can see this pointer. It's going to show basically which part of a propulsion system I'm talking about in a specific slide. So water vapor superheating is favorable for a series of reasons, but I'm going to talk about the ISP thrust power ratio curve. So this curve you are definitely familiar with is the relation between specific impulse and thrust to power ratio. So we know the second equation written here that the product between ISP and thrust to power ratio is fixed. So it gives us this curve, which means that in general, if I increase the temperature, I'm going to increase the specific impulse and reduce the thrust power ratio. For water propulsion systems, it's a bit different since not all the power goes into heating up the vapor, but some of the power also goes into vaporizing the water from the beginning. So the mass flow here is determined by a portion of the power. This m dot equals P vap over delta vap is the vaporization energy. Now we can rewrite the ISP equation as this. And this leads us to this interesting curve, which basically shows that, yeah, the general pattern for high temperatures is the same, but at low temperatures, if I increase the temperature, hence I increase the ISP, I also get a better thrust to power ratio. We can see it better in the next slide. So this one in the same chart, I have on the x-axis, the ratio between the power I use for heating up the vapor to the total power I use. And on the y-axis, a lot of curves. I have the temperature. So I see here, going to the right, I increase the temperature. And at the same time, of course, I increase the ISP. But not only this, up to about 400 Celsius, I also increase the thrust to power ratio. So this basically means that if I'm doing a water thruster, below 400 degrees, it's not even a trade-off. Below 400 degrees, if the higher I am, the better it is, no matter what. If I go above 400 degrees, then I start losing thrust to power ratio. So at that point, it becomes kind of more standard electrothermal propulsion system. Now, we have this basic layout. We understand the fundamental theory. We want to start with the system design of this RCS system. So we have, yes, a bladder vaporization tank and a set of thrusters. What we do here is we have a bit of a schematic in which we study, okay, how much space is each thruster going to take? How much space is each valve going to take? How much space each valve is going to take and how much space the vaporization tank is going to take. We can have a rough idea with the ISP we are targeting from the theory of what performance we can get. So we see from doing basic calculations with the previous theory and considering a typical power budget that one new RCS system may have, we conclude that we can deliver about 3 millinewtons of thrust per thruster with up to 2 firing at the same time. A total impulse in excess of 400 Newton seconds. This delivered thanks to a specific impulse above 100 seconds, which, as far as we've seen, is above anything there is in the industry for small nanosats RCS systems. This is provided with a total power we assume about 25 watt. Now, okay, we have the system. Let's start with the design of the thruster. So what we're doing here is we put a heater at the center and then a channel typical for heating on the outside. What the heater is a particularly high performance model, can hold very high temperatures, and yeah, up to 10 watt on the single heater. The channel, we chose this layout. There are other options, but we chose the annular channel because of the high Nusselt numbers it delivers. So this, we've been simulating it, starting with 2D simulations. The temperatures are shown on the right side. So we start with the heater at 300 degrees and the inlet of water at 50 degrees Celsius. The pause function doesn't seem to work. Okay, and yeah, an inlet stagnation pressure determined by the temperature of the water at the inlet of about 12 kilopascal. So this is what we see, more or less. Here specifically, you can see that the plenum temperature is very close to the ideal values. The Mach numbers are, yeah, hard to see from this, but what basically means is, yes, we can effectively heat water to the temperatures we are targeting. A bit more in detail, we went on with 3D simulations. These ones have integrated the inlet pipe from which the water comes, and there's a bit better contact modeling between the heater and the thruster. As well, in fact, shows that we can get to, if the heater, we manage to hold it at 300 degrees Celsius, we can hold the water at the same temperature. So yes, overall, the performance we've managed to simulate, it's very comparable to what the isentropic calculation, the basic theory I've shown before, gives us. So overall, the conclusion from the 2D and 3D simulations is that an ISP in excess of 100 seconds is a realistic target. So we can deliver the performance we have studied before. Now, about water in the vaporization tank. So how much water I can fit in the vaporization tank? If I just fit as much as I can do with the surface tension, so I just put a few droplets here and there in the vaporization tank, yeah, I'm not going to have droplets, but the thrust is going to go down very fast. The issue here is the volume I can use is very limited, so the pressure depletes and the thrust starts going down, as you see in the bottom left figure. If I feel more than the surface tension allows me, yes, I can in principle hold a nice thrust for a long time, but it's very likely that I'm going to get droplets. And then, yeah, the thrust is going to look like nothing like that. It's going to go crazy and then go to zero when the water freezes. So the solution we came up with is this that we call a LSA, large surface area insert, which maximizes the amount of water I can store in the vaporization tank. Now, determining precisely how much water I can fit by simulation or analytically, it's kind of complicated. So we decided to solve this with the bisection method. Basically, what we did is we placed the target in front of this. We placed everything in the vacuum chamber, and we started opening the valve and see if it releases droplets. And these are more or less the results. Basically, a series of, say, starting with a lot of water, then a lot less, and then going by bisection. We concluded that with about 35 to 40% of the volume filled with water, we can deliver like 0 droplets, which is then going to give us a stable thrust without losses due to the droplets themselves. Now, yeah, this is how we did the droplet detection. So the target may be as well called a piece of paper, and which then was scanned. So water had some pigments which colored it blue. On the left side, you have one of the cases in which you have droplets, and you can clearly see them. On the right side, you have one of the cases in which there's no droplets detected, and yeah, you cannot see that much. So next step, we need to minimize the heat losses. So you can have, in principle, between all of these subsystems, a heat transfer. What we want to do is we want to bring to 0 the heat transfer between the thruster and the storage tank, where the bladder is. because that heat will be then lost to the satellite. As well, we want to minimize the heat loss between the vaporization tank and the bladder, and we want to control between the thruster and the vaporization tank. This is particularly complex because the thrusters are at 300 degrees, while the vaporization tank is at 50. So the idea is using a bracket in which each thruster is mounted, and which holds it to the vaporization chamber. So I can have the little bit of heat I'm gonna lose transfer to the vaporization chamber, which is then gonna be recycled to evaporate the liquid water, and no contact between the thrusters and the tank. Now this becomes an optimization problem. So we want to reduce the heat flux between nozzle and vaporization chamber while maintaining sufficient structural strength. So the bracket and the whole system itself should survive the shocks and vibrations we see during launch. So we started with this design optimization process. At the beginning, we tried to do it with kind of refined methods such as topology optimization or generative design, but it's somewhat complex from the point of view of introducing thermal conditions in these processes. So in the end, we started with this algorithm, which is done kind of by hand, starting with the fundamental drawings and then proceeding with these little design iterations. So in the end, for example, I can show you here on the left is the z-axis shock. This is the von Mises stresses on the bracket. You start by making a given design. You do the resonance survey for the shocks. You see if the stress is okay. Then, if it's okay, you do the thermal simulation. You see if the heat loss is okay. If any of this is not, you restart with a new design iteration until we get to a design that is satisfactory both for the thermal engineers and for the structural engineers. So overall, yeah, I had to blank out the thrusters, but we end up with a design, as mentioned, that can have heat losses to the vaporization tank of less than 5 watts each side. So we're gonna have one of these brackets on each side, and is designed to hold the shocks of launch, so no risk of the structural failure. Next, the thrust measurement experiment. So I can on the top left, you can see more or less the measurement setup. So we measure thrust, pressure, and temperature. We operate these at the mentioned like 50 degrees on the vaporization tank and 300 on the thruster, so which gives us a 12.3 kilopascal of vaporization pressure. This one specifically, we did a pulse duration of about 15 seconds with a duty cycle of 25%. And on the top right, you can see the prototype. This is during leak test, I believe, because yeah, during the thrust measurement, there was a bit too much stuff around. So on the bottom left, you can see we can deliver a greatly stable thrust. So over the single firing, the thrust is basically flat, which if you've seen comparable thrusters, they suffer a lot of this issue of like the thruster going down very fast. The pressure drops a little during the thrust phase and then replenishes when we restart heating up. But yeah, in general, stable thrust performance, which was one of our goals. This case specifically, we were running at about 2.5 millinewton, which as well, very close to the level we are targeting. The pressure, you can notice, is a bit lower than what we were targeting, and I'm explaining in the next slide what happened. So yeah, here you can see the whole duration of the firing. This one is with a single filling. So as mentioned, using the large surface area insert, we can fire for a very long time, a total of 675 seconds, without needing to replenish and maintaining stable thrust over the entire duration of the firing. Overall, yeah, the performance data is shown on the right. You can see that the ISP we managed to obtain is 119 seconds. There's a bit of tolerance, like ±5, but overall, yeah, above our target of more than 100 and well in line with the 3D simulations, which indeed predicted 117 seconds, including the boundary layers. Now, on the bottom left, you can see the vapor pressure predicted based on the temperature of the tank, which is on top. And at the bottom, the measured pressure. So the measured pressure starts a bit lower and then progressively diverges. So in our understanding, there's a bit of mismatch between temperature you measure and the actual pressure and the pressure you are seeing in the tank. So what's happening here is that yes, you heat up the tank, so you try to increase the pressure, but the temperature measured by the sensor may not be exactly the temperature of the water. It can be the temperature of certain parts, which overall means that you get a lower pressure. So the next step will be likely introducing a control loop on the pressure, which will guarantee us the exact thrust that we are targeting. Now, in conclusion, at Trust.me, we have a new water RCS product coming up. It's supposed to look more or less like those here on the right. These are still schematics, but we are in the process of the like component design, which I cannot show you. We deliver stable thrust from this innovative set of water vaporization and storage techniques, such as the larger surface area insert. We are planning to deliver this with the standard 1U form factor as well as customized solution. So the 1U form factor is going to have the performance and specifications I show on the right, on the left. This 3 milliNewton per thruster, total impulse north of 400 Newton seconds, specific impulse north of 100 seconds, and operate at a power of 25 watt. Increasing the size, yeah, the tank, the storage, increasing the storage tank size is zero problem. Increasing the thrust can be as well done without major challenges, of course, depending on the interest of the customers. I finished 5 minutes early, so thanks for your attention. And yeah, if you have any question.
Thank you, Julio, for this very interesting new concept of propulsion systems. So maybe now the paper is open for discussion. Yes. So maybe we can start with Stéphane.
Thank you, Laurent. Yeah, congrats, Julio. This was really impressive, and I really like it, you know, because it started from theory until the product. This is really, really impressive. And congratulations to the whole Trust.me team for this.
Thank you. It's, yeah, exactly. It's a team effort, some of which are not mentioned. I must point out that there's a lot of people, especially the interns, who have worked on this, and they're not mentioned in the author. So thanks to them, especially.
I have 2 questions, Julio. The first one is about the iodine system. You know that Busek is also developing iodine thruster, for effect thruster, and ion engine. Just probably you know it. They never flew them.
Busek, I'm not aware of the flying, or I'm aware of that they are planning to fly, but I need to check the dates. I wouldn't even believe it's gonna happen this year. So yeah, from that point of view, we are still the only one who has flown.
For sure, you were the first, but I was wondering if other people nowadays. The second one is about the water thruster. I don't really, for a customer viewpoint, although I'm not a customer, but what is exactly the advantage of this new water thruster compared to your cold gas thruster with iodine?
Compared to the H25, yes. So overall, you've seen the H25 delivers 75 Newton seconds of total impulse. Of course, it's in alpha U, so we could in principle expand it. This one, the specs we are giving as conservative, say north of 400 Newton seconds, and especially the thrust. So H25, I don't have the number on top of my mind, but it's definitely below 1 milliNewton. This one, if you use 2 thrusters combined at the same time, there's going to be 2 of the nozzles used for delta V maneuvers, and you get 6 milliNewton of combined thrust. So you can definitely do a more faster maneuvers, and all the nozzles are going to be pointing in different directions. So with just one system, you can have all sort of maneuvers you can think about in a very compact form.
Okay, so you have basically more trust.
More totally impulse,
More ISP.
more direct.
But could you increase the trust level of your, so transform your cold gas, the iodine cold gas thruster into a thermal, an electrothermal thruster, so heating up the iodine temperature, and then also increase the ISP and maybe the trust? So
it's all things that are doable. The thing is the level of complexity. So bringing it to the temperatures we are working at right now with the H35 is very complex. And since the iodine molecule is very heavy, the benefit to the ISP is still moderate. With water, you have a sharp increase in ISP. With iodine, we have tried certain experiments in which we heated up iodine a lot, but you end up losing a lot of heat and still gaining ISP within certain limits. So in general, the H35 is wonderful for who needs absolute simplicity. If they need a bit more of a refined product that delivers this sort of performance I've been speaking about, we are developing the RCS.
Okay, it was clear. Thanks a lot. Congratulations again. I really
Thank you.
Thanks, Giulio.
Other question, comments, please? In the audience, I have myself one question. It's a pulse, what you did. I mean, in other words, what fix your duty cycle or the time you have chosen just to separate your?
So the duty cycle I've shown is just one of the many. So we tried duty cycles 50% for sure. I reasonably believe 75 as well, but I need to double check. In general, the duty cycle is determined by the amount of power you can give to the vaporization tank. So the point of the duty cycle is guaranteeing that the pressure remains within a certain level. So if you don't have sufficient power in the vaporization tank, then you're going to deplete the pressure very fast. So the duty cycle keeps basically replenishing the vaporization chamber with vapor.
Okay. Other comments, I see one comment.
I see one from the
Ashley asked.
Yeah.
Ashley wanted to ask a question.
Yeah.
Also.
Please, Ashley, you can.
I think you're muted. Okay.
Hi, can you hear me?
Yes.
I was wondering, as I wrote, if you could maybe talk a little about the MPT 300. I mean, you don't have to tell us, the specific design so we can steal it, but, what's the idea behind the technology? That's a quite high power for a neutral, cathodeless design. So I'm curious about how you guys did that.
So we are proceeding with the development. One thing is, I'm not sure specifically about what I can mention right now. If you want, so tomorrow I'm going to be anyway at the panel discussion. So I can check with Dimitro, the CTO, what I can discuss, because we have news, but I'm not sure what I can talk about. So I'm going to check. And maybe if you ask the same tomorrow, I can respond with a bit more detail. Sorry.
Okay, sounds good. Well, hey, if you put it on the slide, I'm allowed to ask about it, I think. But I'll ask again tomorrow.
Yeah, the thing is, so that's just that it's coming. But what has happened so far in the last few months, I need to check what I can mention.
Okay, great. Thanks.
Thank you, Ashley. Davina, please.
Yes, hi, Giulio. Thanks for the presentation, very interesting. Got two questions for you. Which kind of trust measurement system you're using? You mentioned balance. You're using static balance, dynamic balance?
Yes. So this is a single pendulum balance. It's the same, in fact, that we used for the other ones. It's the easiest balance you can think of, like literally hanging from here, straight pendulum, and the thruster pushing on a load cell. overall, we've been happy with the results from the balance because the balance was designed for measuring thrust from HT5s and MT30. So it was designed to catch even the less than 1 millinewton range. The RCS, so the case I've shown was 2.5 millinewton. We've been picking up to 8, depending on the temperature we set in the vaporization tank. So we are generally happy with the measurement of thrust.
But do you manage to also achieve some dynamic measurement, like being able to evaluate the minimum impulse speed? So because this is a system, and instead the grid one is static.
So the minimum impulse speed, I still have. So the thing is, the balance, samples are relatively fast, but needs to do a bit of averaging. The charts I've been showing are with averaging at about 10 hertz. So each data point you see is like 1/10 of a second. The minimum impulse beat should be say if it's 3 millinewton, we could pulse for between 100 and 200 milliseconds. So it will give you, what's that, less than 1 millinewton second of minimum impulse speed. But the very minimum, I still have to see if we can measure it or if there's just too much noise. And
perhaps if I can ask another quick question.
Yes, please.
When you decide for the design of this thruster, did you do like a market survey to understand what was the thrust range that the market would require? I was curious on how
yes.
Did you choose the nozzle design to get 3 millinewton?
Yes. So we've been speaking with a few customers, potential customers, on what they will be interested in. Their requirements were mostly exactly about the thrust range and total impulse. They didn't seem too much interested, but then we know from experience that in the end clients are always going to want more total impulse. So the general demand was between 1 and 10 millinewton of thrust, I believe. So we ended up with this solution of this 3 millinewton. It's reasonably high, and with the very short pulses we can do relatively moderate impulse speed. One thing, so in principle, if someone really wants a super low thrust to have extremely precise impulse speeds, it's just a matter of making a smaller nozzle. So relatively simple to adapt from that point of view as well.
Okay, thank you.
Christophe, if you want to ask your question.
Yes, many thanks for your presentation, Giulio. It's very interesting because you didn't mention the difference between water and iodine. Here you have a water. It's a unified propulsion system, as you show in one of your slides. It's very interesting for the user because contrary to iodine, you can use all the propellant from your tank within any of the thrusters. So it's there is no drawback for the user. He can use everything. So you should insist on this point because it's very important. With other solid propellant or iodine or other, you may have only half the total propellant used loaded in your system available for the user. I was very interested with your system for attitude control, and for attitude control, thrust is quite high.
So, of course, it's scale dependent. Yeah, I understand.
And so that when you say people were asking for 10 millinewton or 1, that is depending on the size of the CubeSat, of course. It's quite high. So that same question as with Davina. Of course, the order of magnitude for attitude control is 100 micronewton. So
Okay.
you answer something that it could be possible, but you have many losses in the nozzle in that case, no?
Indeed, yeah. The smaller we go with the nozzle, we've seen. So from the thrust measurement, it's kind of difficult to pick it up because you start going very low. From the simulation, we've seen, as you were mentioning, yeah, losses for very small nozzles starts to become worse. One thing that can be done is reducing the vapor pressure. So keeping the vaporization tank at substantially lower temperatures, already, say, going to 30 degrees of vaporization temperature rather than 50, yeah. You will get roughly a quarter of the thrust that we are getting right now. So yeah, this can be considered as well.
Yeah, and you are not obliged to have water. You can have something else like alcohol or something.
Indeed, yeah. We can. I must mention we've been considering the adaptability of this system, and indeed, one in principle can use this with many liquid propellants. It of course depends on the preferences. Alcohol has a higher vapor pressure, so in principle you can deliver more thrust, say at the same temperature. It would sacrifice a bit the ISP, but yeah, it's again a matter of trade-offs.
Okay, thank you.
Thank you.
Okay. So thank you, Julio. So now we have to switch, and so the next speaker is Davina Di Cara from the European Space Agency, and she will talk about ESA activities on CubeSat electric propulsion. So please, Davina.
Thank you. Just quickly share my screen. Okay. Yeah, so what I will introduce to you today is just to give you a bit of an overview of what's going on at ESA in the frame of the CubeSat electric propulsion. And I will talk through the ESA technology strategy, the view that we have at ESA on CubeSat propulsion. We will present some of the results on the study that we did it on what the mission needs are and the market forecast. We'll briefly introduce you also the CubeSat IOD mission with electric propulsion, mention some of the technology program that we are running, in particular in TDE and GSTP, which are targeting development up to high TRL of electric propulsion system for CubeSat. We'll mention also the outcome of the harmonization process with the technology mapping and the roadmap that we are building together with industry, research center, delegates all over Europe. And also the result of the work that the working group is doing at ESA to try to establish dedicated standard and guideline for verification of CubeSat electric propulsion. And also we'll talk about the upgrade that the plan that we have for upgrading the ESA propulsion laboratory, and maybe also some of the result of the workshop that we did it early this year. So for those of you who don't know me, I'm an electric propulsion engineer at ESA, and I work in the Directorate of Technology. And in this directorate, we believe that our responsibility is to make sure that the right technology will be available at the right maturity and the right time for future mission. So we have 4 pillars identified for technology target, which we are working on. And these are to improve the development time of any technology by 2023 of 30%. To reduce one order of magnitude the cost at every generation of the technology, to have a 30% faster introduce on mission on innovative propulsion technology, and to invert the Europe contribution to space debris by 2030. Particularly for what concerns propulsion, we work together with industry and delegates all over Europe to develop in-space propulsion to enable new emerging applications, to enhance the creation of new market, and to enhance the reliability and the competitiveness of the European product. And that's together also with developing, of course, a testing and diagnostic tool, which help us to enhance the capability of independent forecast and validation in order to put the European product in high into the market competition. On CubeSat propulsion, we've been starting at ESA to work on CubeSat propulsion since now quite a few years. We've seen that the CubeSat were originally intended only for educational technology demonstration purpose, but now there's more and more interest. They're becoming very attractive by institutional and commercial users. So especially, and this is for application that span for any kind of space applications, so from Earth observation to telecommunication, information, and also exploration. We also see and witness that CubeSat are becoming bigger, they're becoming more complex, capable to offer more performance payload. And of course, in all this, propulsion capability are becoming crucial to enhance mobility and utilization potential of the future CubeSat. And that's because propulsion are needed for any kind of maneuver, from insertion, station keeping, reposition, and especially for collision avoidance and disposal. These are really two applications that we are looking very carefully, but also more recently for interplanetary transfer. Today, we witness more or less 100 CubeSat being launched every year, but the market forecast an increase on the uses of CubeSat with propulsion in the next 10 years, in fact, in this decade already, up to 300 CubeSat in the next 10 years, with a market dominated by Earth observation and information communication in LEO. We've done a bit of a mapping of what is the state of art of the technology in Europe, and we counted that there are a bit more of 50 CubeSat propulsion systems at the moment under development in Europe, mainly by SNE. Only few are flight ready. A lot of them are still in development phase. And this is for electric and chemical when I say over 50. But the majority, I must say, is in electric. And we have, I believe, over 80, but the number is increasing in the last months, and I'm very happy, of course, of it. So, but so far we could count a bit more than 80 propulsion system, a CubeSat propulsion system, European, being already launched, and this is. Though from few suppliers with a limited return of experience. When I say limited return of experience, it's because mainly there's been used on IOD mission with limited firing time and limited access to flight data. And I mentioned there, of course, everybody know the market is led by Impulsion, but there is also a company like Transme, Exotrail, T4I, and Morpheus. They all have had already their flight experience. We also believe that there is a wide range of mission applications, so there is no propulsion system that fits all. So it's good to have a competition, but it's good not only because of commercial purpose, but because we really see that there is a need of differentiating the technology and to create a portfolio of commercially ready technology to serve the different applications. We're also looking very careful to the regulation, especially on the debris mitigation, because they might impose a mandatory implementation of verified propulsion system in the future, for example, for collision avoidance maneuver and the orbit. And this is really becoming one of the topics of high interest. We have several announced IoT mission. We see a lot of communication of flight future flight opportunity. But we strongly believe at ESA that IOD is not always sufficient to guarantee the high level of readiness, and that ground qualification will be still required. Now, we can always, of course, we're always open to discuss what does it mean on ground qualification, and I will talk about this a bit later on. But yes, ground qualification is still required. One of the points also that we see is that there are no official standards for CubeSat. The ECSS, which is the standard we use at ESA, that we've been using for all the missions so far, they are not applicable one-to-one to CubeSat or to CubeSat propulsion. And that's because this kind of technology target low cost, target fast time to market, and the ECSS can be a bargain on that. So we see that more the need on tailoring or dedicated ECSS, dedicated engineering guideline. But of course, in order to have an agreement of what is the minimum level of requirement that are a must for verification on ground. Strategic to CubeSat, we see that being cost reduction, of course, but also ensuring the performance, reliability, and safety. That's really important. And we believe that the reliability could only be increased by ground testing, or of course, extended the flight time in orbit. Increased production rate, availability or reliable microfabrication technique and control manufacturing, cleanness. This is very important. We also believe that it's important to get access to this flight data of the perform IOD in order to extract the lesson learned. And also we think that it's important to limit the dependence on components subjected to export control. So ideally, a full European propulsion system will be the desire. We also put very high attention on the availability of test facility and test methodology and test equipment. So particularly standardized test methodology and test equipment in order to accurately measure the thrust down to micrometer level, but also transient. Noise, response time, minimum impulse speed for certain EP technology that are important, and of course from the diagnostic. And that mainly to validate the performance and life model, also of technology operating with relatively novel propellant like iodine, and also to verify the functionality of the propulsion system within the rest of the satellite. So at the moment, we are working at ESA on the creation of this independent test center for having an end-to-end testing of CubeSat with firing propulsion. And we believe that this will offer the European industry the capability to put product in the market, which are innovative, enabling, but also very independently verified, and so therefore to increase their competitiveness in the market. CubeSat mission needs, as I said before, that we see CubeSat application in every kind of domain, from Earth observation, including constellation now, telecommunication information in LEO, including also mega constellation, in-orbit services becoming one of the application to look at, navigation, and but also mission for astronomy, science, study of space weather, and even the space exploration. We see the CubeSat becoming bigger, as I said before. At the moment, we look up to 60 new factor, but this might change even in the future. And with all these different applications, as I said before, there is no propulsion system that fit all, and the requirements are really vary widely within the application according to the application. We did a market study together with Euroconsult, and this is a bit of the outcome of that forecast over 300 satellite with propulsion, with European propulsion, because this was targeting European product in the next 10 years. We see the orbiting and collision avoidance capability becoming a more and more hard requirement. And so in order to respond to that requirement, reliability is the word to keep in mind. But we also see new mission coming, interplanetary. And for all that, we have identified that the high delta V propulsion and 6 degrees of freedom propulsion is where we should really put attention on. And okay, this graph will show, again, one of the results of this study, which focused the number of thruster. But of course, I always keep saying that we need to be very careful because this is a market assessment and the market is changed, it's got uncertainty. So, but yeah, we see quite a lot number of thruster, and you can see there also the different thrust level that will be required in the next 10 years. We have a fleet of CubeSat mission at ESA, CubeSat IOD mission, and you can see there the one in green are the ones that are already in operation, the one in yellow, the one in implementation, and in blue, the one in definition phase. And recently we are also including into this IOD mission also demonstration of electric propulsion. And I just mentioned there 4 of them, which I think are the quite interesting one. One is Margo. Margo will be the first standalone deep space CubeSat that will rendezvous with the near Earth orbit and will use a RIT 3.5 grid ion thruster from Mars space to do the transfer to the near Earth orbit, but also a xenon-fed co-gas, so it will be an hybrid system. We have a GOMEX-5, which has got several experiments on board, including one of the iodine-fed MPT-30 electric propulsion system from TrustMe to demonstrate large delta V in excess of 280 meters per second. We have a lunar orbiter with FIP, which is also in definition phase. And we have another mission called Spectre, which is at the moment having a trade-off open on electric propulsion which plan to inspect the large debris in LEO. At ESA, we also have several technology programs, and some of them, they are application driven. And you can see there, we have InCubed for Earth observation, CTP for science, ARTES for telecom, Expert for exploration, FLPP for launcher, and navigation is about to complete Egypt, but the new program is called NAVISP. But then in my directorate, we have technology program, a technology development program, which are independent from the application, so span all over the different application, and they are divided into TDE and GSTP. And TDE, for those those are a bit more senior here in the room, who might remember the TRP in the past, but the objective of the TDE is to develop technology which are in a early stage, so up to what we call a TRL readiness maturity of 4, so breadboard prototype demonstrating in a representative environment. And these are open calls, so you see always this ITT coming out throughout the year with new requests of proposal to European Industry and Research Center. And then we have a GSTP, which instead are optional program, and they take the product that sometimes are developed in TDE, sometimes are developed through other means, but the objective is to take into high level of maturity, even into in-orbit demonstration with this elementary. And here I just have a few slides to introduce quickly some of the TDE and GSTP that we are at the moment running at ESA, and some of them are going to be presented over this workshop. So I will not give a lot of detail, but just I will mention them. And the first one is one with T4I on the upgrade of the Regulus system. Regulus is an iodine-fed electric propulsion system based on Helicon plasma technology, and is also performing its in-orbit demonstration at the moment. So what we are doing with this TDE at ESA is to, together with T4I, is to upgrade the Regulus into E-Regulus. So an higher power system. So Regulus was 50 watt, and now we're going to 150 watt. We are moving to Xenon, and that's because mainly this application is not really CubeSat. The call was open to CubeSat or microsat, but this is more intended for microsat. We have also a contract with Impulsion on the Nano AR3 This is an upgrade with respect to the flight product, to the flagship Nano FIP, and this is introducing a trust vector capability through a segmentation of the extractor. Forgot to mention before, but all this activity, the plan is to perform a definition of the requirement, definition of the design of the prototype, manufacturing the prototype, and then testing, both at the company, but also at ESTEC with an endurance test. So T4I before has already completed the first on the requirement and design definition, and they are at the moment in the prototyping phase. And Impulsion also, they are at the moment completing the assembly phase. And in fact, the plan is that they're coming to ESTEC in the next 2 weeks for starting the test at our laboratory, and this involves performance characterization and endurance. We also have a same contract with ExoTrail that also targeting upgrade of the nano system, which is also flight. The objective here is to extend the life by modifying some part of the thruster in order to extend the life up to 5 kN/s. They are at the moment completing the design and definition phase, and as soon as they will enter in prototyping, and they're planning to come to ESTEC for testing by the end of the year. And the final one we have also in parallel, so we have four electric propulsion activity in parallel, is with University of Southampton, and they are building the first all printed VAT propulsion system. So this is quite innovative, in my opinion, because everything is on a sticker, and I think there is a talk tomorrow about this more. So where we are also with this, we have completed the requirement definition phase. They are at the moment doing some tests at component level, and the plan is also that they're coming to ESTEC for performance characterization and endurance test by the end of this year. We have several GSTP activity this is more for higher, for more mature development. So the first one is with the ExoTrail on the ExoMG microthruster, and this is involving the full qualification with a CDR plan already beginning of next year. And we have a series of activity on the propulsion system for Marco, so on the development and qualification of the thruster, neutralizer, but also the entire propulsion system. We also have an internal activity. This is targeting, for example, for what concerns the RIT, the validation of the life model, so through extents like endurance test. We are also running the harmonization process, and the harmonization on CubeSat propulsion is the first time we actually do it. And there is a reason, of course, the reason is because there is a lot of interest on this technology. The idea of the harmonization is to try to get an idea of the status of the technology in Europe in order to build the roadmap. And the harmonization of CubeSat propulsion include chemical and electric propulsion system for CubeSat that are for CubeSat up to 16U. We have put a target on the thrust level. Mainly this is really applicable to the chemical thruster, but also we include in there all the propulsion technology which we do not follow the ECSS, but they are targeting mission where a bit higher risk is allowed. So we've done a mapping, we've done a survey on the mission needs and the market analysis, and we are at the moment finalizing the roadmap. So in fact, next week we have a meeting with all the delegates to agree on the roadmap, and hopefully this dossier will become available to all the European entity by November. And at that point, if fortunately the European only stakeholder will be interested, they will be they will be able to request a document through the ARMO webpage of ESA. We're also looking at the mapping outside Europe, and we've done a bit of research to understand how the European technology fit into the worldwide market. But in the meantime, also, perhaps most of you know, has released a document on the state of art of technology, which I suggest also everybody to have a look at it. It's available on the web. The roadmap. We build a roadmap based on the identified needs, and we split that into we classify into category. The needs that we have identified is on the development of standard, usage of flight data, rapid advancement of state of art, of the state of art in European CubeSat propulsion. We want to maintain, of course, and build up competitiveness in order to have offering the product, European product, which are low cost, but also high performance and reliable. And we want to ensure independence from European non-dependence, and perform a certain qualification, IOD, etc., etc. So then you will see the roadmap when it will be published, divided in different aim, we call it, and for an overall proposal of 72 new activity and a budget of almost 30 million. We have a standard at ESA, ECSS, but we have also particular tailored version of the ECSS for CubeSat, in particular the ECSS-E engineering standard. We work on a light approach for what concerns product and quality assurance, and with emphasis on verification control, traceability, Kleenex, and risk mitigation. But there is no specific, as I say, standard for propulsion. So we have started working internally at ESA with a team of experts, a bit of from chemical and electric propulsion. And we started this exercise of tailoring existing propulsion standard. So propulsion general, liquid electric propulsion for spacecraft, and testing. We tried to reduce the number of requirements that you can see there are quite impressive, but we're trying to reduce it and tailor it to the application, if it's CubeSat meant for educational demonstration purpose, or if it's a commercial operational CubeSat. Keep in mind always that the technology target low cost and target fast time to market, but also considering the safety of the product. We also started working on drafting a guideline and handbook, mainly for verification, try to indicate what are the minimum level of verification that we believe are still important to carry out on ground. And with a list of minimum set of documents, we know that ECSS can be quite heavy on documentation part. So we try to really string to the minimum of what are the documents that are necessary and what is the content of each document that are necessary. And we also put there a bit of a trade-off on what to do. Endurance tests, life tests, this is a big question mark. And we believe that there are certain criteria which are listed there that help deciding if an endurance is sufficient or is a full life test is required. And that's, of course, depending on the qualification status, number, level of tests that has been performed on ground and flight heritage, the maturity of the technology, if an accelerated test can be done, but also cost and programmatic are to be considered. Just very quickly on the plan that we have to upgrade the
Davina, 5 minutes. Yes, 5 minutes, please.
I think I will be in the 3 minutes. We have, for those who don't know, we have already 7 chambers at ESTEC in the Netherlands. They are already suitable for testing a CubeSat propulsion, perhaps not the one with operating with iodine yet. So what we are doing now, we have submitted an internal plan to upgrade this laboratory, and with an incremental methodology. So we will deploy certain service in the next years. So the first would be to upgrade one of the facility into TVT tests, so in order that we could perform an end-to-end test, so of the entire CubeSat satellite with the electric propulsion on board and the electric propulsion firing, so the firing TVT test. We have also planned to upgrade one facility to offer EMC/EMI test, and because this we believe is quite also important, and also plan to upgrade the diagnostic and thrust measurement equipment in order to serve the market at the best. And in the long term, we also even look at perhaps including a solar simulator in one of the very quickly on, we have this workshop in April. Some of you attended. We had quite a large audience, up to 400. This was limited to only Europe, so it was quite interesting to see the interest that there is on the CubeSat propulsion. And out of this workshop, we got again a check on the state of art of the technology in Europe, on the market assessment. We see that in fact our market assessment perhaps was a bit underestimated. There was, we see that there are a lot more orders, which is very good, of CubeSat electric and chemical propulsion system for CubeSat in the next decade. We have highlighted what are the main requirements that customer want: high delta V, 6 degrees of freedom, but also reliability, safety is very important, and life test and end-to-end test are really considered important by the customer as workmanship and the risking activity. And we have asked a few questions during that workshop if the ECSS, if they are still in use, and in fact the answer is yes. Companies still use ECSS, but they would like to have a dedicated one, and also an handbook. It is very welcome. And we also ask if that our plan of building this test center at ESTEC, it's of interest for industry and research center, and the answer was yes. When you see there, the answer is not the number of people that voted, but in fact it's the number of organizations. We try to only count one vote per affiliation. So it's really interesting to see that high number of companies, they have responded yes to our question. And also this slide gives a bit of a view of what industry or research center see needed for the future in terms of test capability. Thrust vectoring measurement, EMC/EMI test, endurance life test is the main interest. With this, I conclude. I hope I gave you a bit of an overview of what is the ESA technology strategy and the ESA vision on CubeSat propulsion, and also a view of what we are working in the frame of the harmonization process, the mapping, survey of the mission need, the market forecast, and roadmap. Also show you some of the IOD mission with electric propulsion. So I only took there the one with electric propulsion, and give you some information on the running activity that we are doing, and on the result of the working group on the ECSS engineering, tailoring and guideline, and a bit of the conclusion of the workshop that we had early this year. So at the moment, after assessing all the propulsion system for CubeSat, and after discussing with a national agency and industry through workshop, conference, and also direct contact, we are working on this creation of an independent test center for CubeSat propulsion within the ESA propulsion laboratory. And I think I can conclude here, and I take any question.
Okay, thank you, Davina, for this large overview of these activities on CubeSat and the propulsion system. And so now we can have maybe some questions from the audience. And I see Stefan, please, you can start.
Thanks a lot. Thanks a lot, Davina, for this very comprehensive overview of ESA activities and capabilities. It's really impressive. I mean, I'm always impressed. And I've been seeing also the evolution over the last 20 years. So this is really, really great. I currently
know each other since a long time.
Yeah, right. I currently have two questions. The first one is about the test center you talk about, the idea of having a test center, which is of course a very good idea. I'm just curious about the limit that you have in mind in terms of CubeSat power or size that could be tested in this center.
Yes, at the moment.
You said that the size is increasing.
The size is increasing, but we had, of course, to put a limit that in this first phase, because we have to start from something, and the limit will be 16U. So 30 kilograms satellite. So the plan is, I mean, you know, the facility is planned to, the first plan is to upgrade SPF, which is one of the largest facility that we have at ESA Propulsion Laboratory, to make it thermal vacuum compatible. And this is a plan that we are at the moment in execution. So hopefully by the first quarter of next year we'll be commissioned, but we are also facing some delay due to the COVID, due to the but yeah, that's the plan is to target 16U for electric propulsion and for chemical propulsion. So there will be, of course, on the chemical propulsion side, we are looking only at the green propellant at the moment, but there is also a plan for the chemical propulsion colleague to establish their own facility outside the ESA Propulsion Laboratory, because if they start, they need a bigger one. But the idea is that the thermal vac facility next year will be available to electric and green propellant propulsion.
Very impressive. I have a second question regarding the outcome of the workshop you've been organizing. So you went very quick, of course, but at one point you said that people were interested in a handbook.
Yes.
About what? I'm just
the handbook is a bit of a guideline. So the ECSS, the way the ECSS is structured, there are standards which are basically requirements. So for propulsion, for example, we have a list of a set of requirements which are in the standard. But then we have a handbook or guideline which tell you, they're not requirements, but tell you how to demonstrate a requirement. So the idea of this handbook is to, and it's not something that we want to write by ourselves at ESA. At ESA, we want to involve all the institution, industry, to build it together in order to say, okay, how do we demonstrate certain requirement? How do we demonstrate the trust? How do we demonstrate life? Of course, for example, if you take life, it's the easy example. The ECSS tell you each propulsion system needs to demonstrate on ground 1.5 the life that we'll have to do in space. So this is a bargain for electric propulsion. We know very well that on the bigger electric propulsion system, it takes a long time, it's super expensive. And so we have to find a compromise because doing nothing is also bad, because it means that we are launching a product which are not reliable enough. I mean, we cannot be confident on what will be the final life, but also doing a full life test is also not possible to stay within the cost and the time to market needs. So we have to find a compromise and to what is the best. And that's what the handbook is meant to tell. So to find an harmonized and a compromise which is acceptable by the agency, by the customer, and by industry, and by research center, by everybody together. So that's the idea.
Okay, that's a very good initiative.
Internally, but we will open up to external as soon as possible. So we are at the moment trying to define the way to involve the community.
I see. Thanks a lot, Davina, and I hope to meet you soon at ESA.
Yeah, hopefully when this time passes, we are really happy to open the door again. Because,
great.
It's needed.
Thanks a lot.
Okay, thank you, Stefan. Thank you, Davina. Other questions, other comment, please, in the audience? I think that we need a break, no? It seems. Okay, so I think that if there is no more question, we can maybe make have a break now, okay? And we come back at 11. Okay.
Thank you very much.
Thank you, Davina, and thank you, Julio, for your both presentations. Thank you.
Thank you. Bye.
Stéphane, tu es là?
Oui.
Ouais, je vois qu'il y a des personnes qui sont passées en spectateur, en fait, de la session, pour la session suivante.
D'accord.
Ouais. Je te passe la main, enfin, je les passe en panéliste.
Ouais.
Ouais. Alors, attends, faut que je les retrouve. Maintenant que je les ai vus, je les retrouve. Ah, si, ça y est. Je pense que je peux les. Voilà.
Oui, tu peux les changer.
Ouais, ça y est, j'en ai fait. Merci, Pina. Hein?
Qui c'est qu'on a de l'ONERA?
Et je sais pas, c'est que je me posais en direct là. J'arrive à promouvoir. Ah, j'y arrive pas.
C'est Marlène là.
Oui.
De l'ONERA, normalement, je vous entends. C'est Victor Desangles.
D'accord.
Est-ce que vous l'avez dans les participants?
Oui, je sais pas. Pour le moment, j'essaie de passer. J'arrive pas à le passer en panéliste.
Non, c'est pas panéliste, c'est animateur.
Non, mais je veux dire la personne qui est un spectateur, qui est en fait est orateur.
Est-ce que vous. Ouais. C'est toujours vous qui êtes animateur, Laurent?
Je pense, je sais pas. Ben oui, il y a pas de...
Oui, c'est toi.
Ouais.
Tu parles de Li?
Oui, il y a Li et il y a Dungo aussi. Do. Je vais essayer Li. Oui. Plus promouvoir aux panélistes.
Ouais.
Oui, hier, ça marchait.
Là, ça marche pas.
Et ça met un petit peu de temps des fois parce qu'il faut que. En fait, eux, ils ont un pop-up, je pense, sur leur écran et il faut qu'ils acceptent. Hein, donc peut-être que
d'accord,
vous.
pardon. Ah oui, pardon. Peut-être que je sais pas. Ah, ça y est, peut-être.
Voilà.
Il y en a eu un, mais je ne le vois plus.
Parce qu'il est en train d'arriver. Voilà.
Ouais, il arrive.
Ah, ok,
il est arrivé,
parfait.
Li.
Et vous reste Gaëtan où, c'est ça?
C'est ça, oui. Donc, on va voir. Ok, je pensais que c'était automatique.
Thibaut, qu'est-ce qu'il fait?
Hi.
Hello.
Hello.
Hi, Li.
Hi.
Do you hear me?
Yes.
Yes.
Okay.
It's the break, so we will restart at 11 p.m.
At 11.
Time, so in 20 minutes.
Okay.
And you will be the first speaker.
Okay, thank you.
Thibaut, il faut que j'aille le voir.
Ça y est, ok. Et alors, il manque qui? Thibaut, tu le vois?
Ouais, mais je vais le voir, le bureau d'à côté.
D'accord.
Donc,
et après, de
l'ONERA, mais je
l'ONERA, pardon. Je ne vois pas qui.
Donc, vous ne voyez peut-être pas arriver.
Ouais.
Je vais vérifier sur le papier qui c'est qu'il y a d'autres.
Ouais. Je te passe les droits, Stéphane. Allez, plus. Nommé animateur. Ça y est. Oui. Voilà, ça y est. Bon, à tout à l'heure.
Bon café, à tout à l'heure.
Ouais.
Un grand café.
Bonjour.
Bonjour. Bon, tout est là de marcher correctement à nouveau. Bien.
Stéphane?
Oui.
Okay.
Ouais. Tu as des nouvelles pour la table ronde de ce soir? De Francesco?
Non, on va lui envoyer un mail.
Non, parce que là, hier, il nous a envoyé, en fait, hier, il nous a demandé des bio, quelque chose, tu vois, quelques trucs. Je viens de renvoyer quelques lignes là, mais je me rends compte que autant c'est la technologie a pas mal avancé, j'ai l'impression.
Est-ce qu'il avait contacté tout le monde?
Eh ben, je pense que oui. La liste qu'on lui a donnée, oui, mais j'avoue que je ne sais pas.
Bon, ben, envoie-lui un petit mail là, et puis.
Ouais, ça y est, je l'ai fait. Je l'ai fait. Demandez s'il y avait des retours.
Ça marche.
Ouais, je l'ai fait, ça y est. Parce que je dirais que j'ai rien vu passer, quoi.
Ça marche.
Demain matin, ça sera toi qui commencera, ça te va? Ouais, parce que tu sais, il me tanne là pour que je refasse la session pour l'ICOPS, la training session.
Ok, oui, tu
C'est de 8 à 9. Non, mais ça devrait aller, mais je me méfie à ces trucs-là.
Non, mais c'est bon, je fais la première.
Ok, d'accord.
Ok, ça marche.
Merci.
So, good morning, everybody. For the second part of this Thursday morning session, after two very interesting invited lectures. So in this fourth session, we will have four presenters, four speakers. Three talks will be devoted to Hall thruster and low power miniaturized Hall thruster. And the last one is about ECR, electron cyclotron resonant thruster, and it will be given by Onera. So the first speaker of this morning is Dong-Ho Lee from Korea. From the KAIST in Korea. So Lee, it's up to you.
Yes.
We see your slide. You've got 15 minutes. Okay.
Okay.
We'll give you a sign. I will interrupt you 2 minutes before the end. And we will have time for a few questions. So I leave the floor.
Okay. Thank you for the introduction. My name is Dong-Ho Lee from KAIST in South Korea. Today, I'd like to talk about the comparison of 250-watt class micro-Hall thruster with different magnetic field configurations. And in particular, we found large differences in both performances and diagnostic results. And the details will be discussed in this presentation. And most of all, microsatellites with the mass of less than 50 kilograms are highly utilized in these days because of their low cost and short preparation period. And these microsatellites particularly have high potential for various space missions, as well reported so far. And that's why the importance of such low power electric propulsion is getting more increased these days. And we believe Hall thrusters can be one of the options for the operation of these microsatellites because of their high thrust power ratios and as well as their high specific impulses when compared to other electric propulsion systems. So the thing is, when we operate these Hall thrusters in low power region, like sub 100 watt classes or 100 watt classes, they inevitably show lower thrust performances as shown in this view graph, mainly because of the increased surface to volume ratio of plasma. And that's why we think we still need to study on these micro Hall thruster plasmas to further understand the underlying basic physics, which might be a little bit different with the higher powers, and to further enhance the performances of these micro Hall thrusters. Actually, in this study, we developed a 50-watt class Hall thruster, which provides T over P ratios of thrust to power ratio of 64 millinewton per kilowatt with anode efficiency of 30% at 64 watts, which is quite competitive when considering the operation of sub 100 watt classes. And here's the details. We actually compared two 50-watt Hall thrusters, which have exactly the same outer structure as shown in this figure, but they have two different magnetic field lines. The first one is the conventional Hall thruster with radially dominant magnetic field lines. You can see the detailed field in this figure, and we designate it as KHT20 here. And the other one is a field-tailored Hall thruster with partially wall-grazing magnetic field lines. You can see the convex shape towards the anode here, and we designate it as KMHT20, well, the letter M just simply means magnetic field tailoring. So in this presentation, I will just call these Hall thrusters as KHT20 and KMHT20. And for the whole experiment, we used a vacuum facility which provides a base pressure of 6 times 10 to the minus 7 torr, and the operating pressure was maintained below 8 times 10 to the minus 6 torr at the 0.49 milligram per second of xenon gas supply. And for the thrust measurement, we used a pendulum type thruster stand, which provides an inherent error of plus minus 1.7% within the thrust range of 2 to 5 millinewton. You can see the raw data here. And for the diagnostic tools, we just use some standard diagnostic tools for electric propulsions, including Faraday probe and RPA. And we also utilized an E+B probe for multiply charged ion current. And we also used an LIF system for IVDF. We actually measured the IVDF at different axial positions and radial positions as well, which will be discussed in later. So this is the operation result of our 2 50-watt Hall thrusters. And most of all, a stable operation was found within the power range of 30 to 70 watts for both thrusters, and at the mass flow rate condition of 0.27 to 0.42 milligram per second. And one interesting point in this operation was that there was a distinct discharge mode change in KMHT20. And you can see the IV curve here, where which shows the operation of 0.42 milligram per second in 2 thrusters. And when we increase the voltage of KMHT20 from 160 volts to 200 volts, we observed a distinct discharge mode change in KMHT20, which led to an increase of only 2 watts of anode power at here. And at the same time, a large localization of ionization and acceleration profiles were observed right near the axis plane. And this eventually led to a large beam narrowing by 24% and thrust enhancement by 14%. The details on this mode change, as well as the changes of acceleration or ionization profiles, can be found in our recent paper. And actually in this study, we actually compared the operation of the 2 thrusters over 60-watt operation in blue area here. And particularly, we focused on the comparison of 200 voltage conditions, which is in the blue circles in here. And we decided to try to figure out what's really different between those 2 Hall thrusters. And most of all, for the first step, we measured the thrust performances. And we measured the thrust and plotted the thrust performance along with the anode power. And as you can see, KMHT20 showed higher performances than in KHT20 at over 60 watt operation. So particularly at 64 watts, 14% higher thrust was observed in KMHT20. And when you compare the 200 volt conditions marked with the blue circles in here, it turned out that KMHT20 can save approximately 9 to 10 watts of anode power to generate a similar level of thrust performances when compared to the KHT20. So consequently, we got the thrust of 3.8 millinewton and 920 seconds of specific impulses, and 29% of anode efficiency, and finally 63 millinewton per kilowatt of thrust to power ratios at 61 watts of operation. And we further investigated the plume properties by using the Faraday probe in KMH20 and KST20. And we found a large beam narrowing in KMHT20, as well as a decrease in propellant efficiency. Again, as you can see in the 200-volt condition marked with the blue circles in here again, you can see a large beam narrowing in KMHT20, which is by 33%, and a decrease of this propellant efficiency by 19%. This means a lower ionization, but a large beam narrowing as well in KMHT20. And for the other efficiencies like voltage or current efficiency, they were not distinguishable in this experiment. And then we also calculated the theoretical thrust by using the diagnostic tool, diagnostic results shown in the previous slide, and then compared the calculated thrust and the measured thrust. And we found a nice agreement between those two thrusts. And actually, we calculated the thrust by using this relation where the blue colored parameters are from the diagnostic tools. And we also found that the ion current times beam divergence term is quite similar for both thrusters at 200 volts, which means a lower ionization can be compensated by a large beam narrowing in KMH20. So consequently, the power was decreased due to the lower ion current and discharge current, and as well as the beam became very narrow, and this finally led to a similar thrust performance at lower power as much as 9 to 10 watts in KMHT20. We further investigated the ion velocity profiles by using the LI system. And actually, we measured the IV depth along the mid-channel axis from z equals -6 to +5 millimeter from the axis. And then we found a narrow ion acceleration profiles in KMH20 with the larger maximum and sharper profiles of electric field in KMH20. And we believe this large electric field and sharp profile probably affected to the larger axial component of ion current, which led to a narrow ion beam as shown in the previous slide. And we also investigated the ion density profiles along the radial direction in the two thrusters. And first of all, we actually took a photograph by using a Xenon 2 ion filter and found a distinct dark gap between the plasma and the wall in KMHT20. And then we measured the IV depth along the radial positions and plotted the peak velocity of IV depth along the radial direction. And we found those peak value of IV depth gradually decreased near the inner channel while it maintained more uniformly in KST20. And because the peak value or intensity of IV depth suggests the relative metastatic ion density, and these ion densities are quite related to ground state and shows a similar trend with each other, we speculate a less ion density near the channel wall of KMHT20 or a more uniform one in KST20. Actually, this kind of dark gap is also found in several magnetically shielded hole thrusters before, so we believe this is kind of from a similar phenomenon here. So in summary, we compared two 50-watt class hole thrusters with different magnetic field configurations. And it turned out that the field-tailored hole thruster or KMH20 saves up to 9 or 10 watts to generate a similar performance, or at the same time, or in other words, the field-tailored hole thrusters showed higher performance at the same power when compared to the conventional hole thrusters. So it eventually showed 4.1 millinewton and 1000 second and 31% at 64 watt. And the correlation between the ionization / acceleration profiles and performances will be investigated. Thank you.
Thanks a lot, Dong Ho, for this presentation, interesting presentation about miniature old thruster. You were perfectly on time, which is pretty great. Are there any questions from the audience? We have 5 minutes now, so we have time to ask a question. So I will ask the first question. So you are comparing two different magnetic field topologies, but how did you select them actually, or how did you select the differences between the two topologies?
How did I select the topologies?
Why those topologies?
Well, the first one, the KST20, just we try to follow the conventional Hall structures like SPT type, which has radially dominant magnetic field lines. And the second one, the KMHT20, we just try to make convex line so as to create the channel wall, because to reduce the plasma-wall interaction. And we just decided to what's really going on when we make these kind of magnetic field lines.
And so basically you think that what the increase in performance and is due to the fact that you better confine the ions and that you have less losses at the wall with the red configuration?
Yes, I'm sorry?
You think that the better performances of the tailored configuration is due to the fact that you better confine the ions and that you are reducing the wall losses?
Yeah, sure. I think it's related to like wall loss, and we found a large beam narrowing in KMHT20. And we believe this kind of beam narrowing might be related to the larger electric field intensity inside the channel.
Okay. Thanks a lot. So we've got a question from Burak Karadak.
Hi, Mazur. Can you hear me?
Hey, hi, Burak. Yeah, great to see you here.
Thank you for this great conference. You kind of answered my question. I was going to, because I'm very curious, the efficiency of the thruster increasing from 15% to 30%, from 50 watt to 65 watt. It's just 30% change in power, but efficiency is 100%. So it's a great change, and I'm very curious the reason. But you mentioned some possible reasons. So okay. But if you have any other comment other than the other potential reasons can be, other than beam efficiency, or do you have any other ideas that can cause this great efficiency increase?
You mean
from 50 watt to 65 watt? Why it increased so much? You just increased the power 30%, but efficiency increased 100%. Is there any kind of experimental uncertainty, or it's just
you mean from this point?
If you look at the plot, you see efficiency at 50 watt is around 15%, right? And it increased, and when you just slightly increase the power, it goes up to 30%, and that is a great change. And
very sudden.
Right.
I see you have some simulation from your group in the next day. Maybe do you have any insights from the simulation that can share now, or any?
Yes. Actually, we have studied this kind of mode change and what really happens at the mode change in our first paper, and consequently, we found a large localization of acceleration and ionization in this mode change, along with a large beam narrowing and along with the electron confinement. So of course, we do not have any concrete numerical evidence yet, but we think those kind of differences in acceleration profiles led to the large enhancement of the thrust. And the reason it seems to be a little bit rapid here is because the discharge current as well as the ion current was decreased when these load change occurs, as you can see in the first view graph in here.
Okay, so the discharge current is decreasing and the beam is focusing. That's kind of okay. Thank you.
Yep.
Thanks. Thank you.
Thank you.
Okay, Dong-Ho, thanks a lot for your presentation. Thanks a lot for answering all the questions from the audience. Oh, there is a lot.
Okay. Thank you very much.
Please, Christophe, do you want to ask it quickly?
Yeah.
Very quickly. Thank you for your presentation. Well, when there is an increase of performance, always the final goal is at the end of the lifetime. And we could saw in the past that it's not evident from the first test that it's going well, but what do you think about the lifetime? At the end of the lifetime of your thruster, do you still will have the same increase of performance?
You mean the lifetime?
Yes, the influence of the lifetime.
Well, actually, we couldn't have any chance to test the lifetime in this study, but yeah, maybe we can test it later. Yes.
Okay, I understand.
Yeah.
Yes. Yeah. Of course, you are at the beginning. Okay.
Yeah.
Thank you.
Right. Yeah. Thank you very much.
Thanks a lot. So thanks a lot, Dong-Ho, for this interesting talk about miniature hole thruster. So now it's time to switch to your colleague, still from South Korea, from CAST. So Wentai, I think, yeah, it's up to you. We can see your slide. It's perfect. So again, you've got 15 minutes, and then we will have 5 minutes for question afterwards. It's up to you.
Thank you for introducing me. Can you hear my voice?
Yes.
Hello, this is Guntedo, a student at KAIST. And today my topic is structure of the ion acceleration region in cylindrical Hall thruster plasmas. In this presentation, I will focus on the ion kinetics, including the ion acceleration and ion velocity distribution function. And these are the content. I will introduce about cylindrical Hall thruster at first. This is the flow graph of conventional annular Hall thruster and cylindrical Hall thruster. You can see that there is no internal parts in CHT, and the magnetic field is formed as the diverging field. So because this magnetic field is very different to annular Hall thrusters, we can expect some unique plasma features in this plasma. Our previous study showed that the propellant efficiency of CHT exceeds the unity in typical conditions. This plot shows the ion current fraction of each charge species, and this shows that the fraction of multiply charged ions account for about 40%. So this is the reason why this propellant efficiency exceeds the unity. And this large fraction of multiply charged ions contribute to the thrust above 30%. So we all know that magnetic field controls electron transport, and it should also largely affect the ion kinetics in Hall thruster plasmas. As this figure shows, CHTs have significantly varying magnetic field topology inside the discharge channel. So we can expect also the ionic feature should be very unique. In this study, we investigate the ion kinetics, including the acceleration and velocity distribution function in CHT plasma. And the non-perturbative ion diagnostic is used. To do that, we employ 2D laser induced fluorescence. We used it for local measurement of GNO plus ion velocity distribution function. This is the use transition of GNO plus, which is the most popularly used for LIF study on GNO plus. And this is the block diagram of setup. Diode laser produced the laser beam, and it is split into the axial and radial beam. And these were aligned to perpendicularly intersect at the probing volume. To do so, we obtained the axial and radial GNO plus IVDF at once, and this is the same example of data. The used CHT has a diameter of 50 millimeter, and the experimental variable was anode voltage and flow rate in this study. So the anode power was controlled in this range. And the value in the parentheses indicates nominal value during the experiment. This figure shows the top view and front view fluorescence collection. To investigate the channel inside, we measured IVDFs as deep as possible we can, but the probing available probing region is restricted by the angle of fluorescence collecting length. It was 32 degrees, and for example, we can measure up to 16 millimeter inside along the thruster axis. Now let's see the results. This is the axial IVDF and radial IVDF along the thruster axis. We define the axial coordinate as G, and it becomes 0 on the axis plane. So as going downstream, we can see that the axial velocity increases, whereas the radial velocity stays near to 0 with the decrease of Phillips-Hop maximum. Because the radial velocity is much smaller than the axial velocity, this increase of axial velocity should be the ion acceleration. So we can say that ion accelerates up to 70 millimeter. This figure highlights the different ion acceleration between AHT and CHT. This is the ion energy profile. So as other studies have shown, AHT showed a narrow ion acceleration region about 10 millimeter near the channel exit. But CHT showed that the ion acceleration front stays at minus 15 millimeter, very deep inside, and it saturates at about 70 millimeter outside the discharge channel. So we can say that the ion acceleration region is significantly extended in CHT plasmas. To check that property, we varied the ion anode voltage and flow rate. These are the plot of ion energy divided by anode voltage. This is for different anode voltages, and this is for anode flow rate. From this figure, we can recognize that the structure of ion acceleration region does not change much by the change of anode voltage or flow rate. So we can conclude that this extended ion acceleration is the characteristic of CHT plasma. In detail, the increase of anode voltage made the ion acceleration becomes more efficient, and the increase of flow rate pushed the acceleration front downstream and increased the ion energy in the plume region, but it saturates above the nominal condition 7 SCCM. This is the 2D RF measurement in CHT plasma. Scales are measured points. Column map indicates the summation of the axial energy and radial energy. Arrows are ion velocity vector, and yellow dashed curves illustrate the ion trajectories. And we can see that as the radial position increases, the ion divergence also increases. And this figure compares the electric field along the trajectory 1 and trajectory 4. We can see that as the radial position increases, that the ion acceleration becomes narrower. In addition, we can see that equipotential contour significantly deviates from the magnetic field line. This equipotential contour should be similar to magnetic field line if the assumption of isothermal property of electron is correct. So we think that this assumption should be used cautiously in CHT plasma. From now on, I will talk about these are IVDF at different axial positions. We can see that inside the discharge channel, IVDF can be represented as a single Gaussian function. But during the acceleration, it becomes significantly asymmetric, and it can be represented as a double Gaussian function. This double Gaussian worked very well in other positions, so we suggested a fast and slow ion group in CHT plasma. This is the fraction of slow and fast ion groups, which indicates the area in the IVDF. And this is the ion temperature of two groups. We can see that the fraction and ion temperature of fast group significantly increase this gray shaded region. And this corresponds to the region where the ion energy increase is very large. So we think maybe the cause of this asymmetry should be significant in this region. This is the IVDF along trajectory 4. And we can see that the asymmetry is not as strong as trajectory 1. So we think that the cause of asymmetric IVDF should be weaker away from the thruster axis. And this is supporting data for that claim. This is a filtered emission intensity obtained by the front view photograph of thruster. The x-axis is the radial position and y-axis is the emission intensity. This is obtained with a 10 nanometer bandpass filter. So this emission indicates the emission of xenon plus, and this is for xenon neutral. You can see that these profiles are very similar except for the axis. So in this region, xenon plus signal is very strong, but genome neutral signal is relatively weak. So we think that the ionization is very strong near the channel, near the thruster axis. So we guess that maybe the instability should be strong near the channel thruster axis. And it can be the cause of asymmetry. Yeah. So these are possible causes of that asymmetry of IVDF. We think that first candidate is ion transit time instability. Our previous study observed that large population of ions that exceeding the anode voltage when the ionic timescale instability is very strong. And this instability is also observed during my experiment. And the second one is by multiply charged ions. Our previous study showed that multiply charged ion current is about 40%. So, and the 2D axial emitter peak simulation showed that the increase of multiply charged ion fraction induces axial electric field instability, and it increased the velocity and dispersion of genome plus ions. So it can be the second candidate. But to be specific, we think that further study is required. So this is the summary. We studied ion acceleration region in shaded plasma using RIF, and the major point of this study is the observation of extended ion acceleration region in shaded plasma. So this is the end of our presentation. Thank you.
Thank you very much, Quentin, for this interesting talk, and that clearly shows also that how LIF spectroscopy can be powerful and useful for our community. So we have a few minutes for questions from the audience. I can start on slide 14.
This slide. Yeah.
No, the previous one. Yeah, this one. On the next one, 14. Yeah. So you show two distribution function far away from the axis. So one is obtained at -5 millimeter and the other one far downstream at 40 millimeter.
Yeah.
The red one measured far downstream, you have a population around 0 velocity. If you look at the red curve, you have a ion group with very low velocity.
This one.
Yes.
Yeah, yeah.
Can you comment on that group? Yeah.
Well, I'm not sure about this. I just can suggest the possible candidate. So I think one thing is about 100 kilohertz ionic instability, because that some peak simulation showed that very low velocity ions occur by that instability. And I also think that charge exchange collision can be the reason why these are appear. Yeah.
And in your explanation just before the conclusion, you were mentioning two possibilities or two explanations: ion transit time oscillation and two-stream instability.
Yes.
Do you know how we could experimentally distinguish between the two possibilities? Is there a way to I would say to really to distinguish between the two and to really better understand which one is at the origin of the distribution function you see?
I have never thought about that, but which one? I need to think about that more. Yeah, I'm sorry.
Fine with me. So now we have also a question from the audience. So Laurent.
Yes, thank you, Stefan. Can you come back, please, to the previous one, to the previous slide? Yes, I was wondering, you know, about the hypothesis that we make in most of simulation, I mean, almost hybrid simulation, about, you know, this equipotential, meaning that we assume a constant electron temperature along the magnetic field lines. And you show here that it seems that you have some deviation, meaning that your electric potential lines deviate from your magnetic field lines, it seems. I'm less familiar with the magnetic field strength in cylindrical Hall thruster. If you take, for example, at Z equal 40 millimeters, what is the magnitude of magnetic field?
Magnetic field is very weak in this region. Maybe I don't remember the value, but it should be lower than 10 Gauss. So
yeah, okay. That could be maybe an explanation why, because, you know, just to maintain this equipotential approximation, you need a very high magnetic field, meaning high magnetized electrons. If you are far away in the region where you have less magnetic field, then you can finally your electron temperature can finally deviate from this magnetic field, because again electrons are less attached, I would say, to magnetic field lines. Okay, yes. So it could be an explanation. Yes. Okay, thank you. Nice, very nice presentation, by the way.
Thank you.
Thank you, Laurent. Do we have any other question? There's something in the discussion. Yeah, good point, Laurent from Mono. No, there's no more question from the audience. Okay, so thank you again, Gunther, for this interesting talk about CHT and the use of LIF.
Thank you.
Time to switch to the next speaker.
Yes.
Okay. So the next speaker, so it's again a talk on miniature low power Hall thruster. And our next speaker is Thibaut Alouin from Exotrail and the CNRS. Okay, Thibaut, we see your slides. So that's perfect. So you've got 15 minutes and you will have 5 minutes for question afterwards.
Okay, thank you, Stefan, for the introductions. So hi, everybody. Thanks for being here for this presentation, which will focus on the plume measurements made in a cluster of 2 100-watt class permanent magnet Hall thrusters. Without waiting, let's start with the motivation. So why is it interesting to make such measurements in a cluster of 2? The first motivation is that it allows us actually to verify if a cluster properties and performances can be determined from one single thruster operation. From an industrial point of view, it's really interesting because you only need to characterize one single thruster, and then after you can extend this characterization to a cluster of 2 or 3 or whatever the number of thruster in the cluster. So to do that, you have different diagnostic possible. The first one is the Faraday cup, so to determine the ion density angular profile. The second one is the retarding potential analyzer, which gives some interesting feature concerning the ion energy distribution function. You can also determine the plasma parameter, so the plasma potential, the electron temperature, and the electron density thanks to long mirror probe measurements. And also some thrust measurements actually to give information concerning the thrust of a cluster of a single thruster operation. Also, on a scientific point of view, such measurements can be really interesting to understand the interaction between the 2 plumes of the thruster in the cluster. And it gives you information concerning the plume arrangement. Basically, so you can determine that thanks to the previous diagnostic that I was giving you, but also thanks to a Crosby probe measurement and laser-induced fluorescence spectroscopy. So for now in this presentation, so I will present you the experimental setup, but also the two diagnostics, basically the Faraday cup and the retarding potential analyzer, which give good information concerning the total ion current and the ion energy distribution function. Concerning the thruster that was used, so it's an experimental model. It's the ISCT 100 V2 developed here in the ICAR laboratory. It's an experimental model, so there is some differences with a flight model. Basically, the gas injector is a ceramic. It's made of mulite, a porous ceramic. The anode is just a ring in the discharge channel, and the magnetic field is generated by permanent magnets. And the channel wall material is made of BnSCO2. Xenon was used as propellant gas for both the cathode and the anodes. An external 1 ampere class LABC solo cathode was used. At the beginning, actually, we were supposed to use 1 cathode per anode block, but the problem is that we have some trouble with one of these cathodes. So we didn't have the choice to use only 1 cathode shared for the 2 anode blocks. Concerning the cathode, the CRP was kept around -10 volts by keeping a constant heating power on it, so that we limit the influence of the cathode operation on the plasma plume properties. Concerning the anode also, various operating parameters were tested. So from this presentation, I will only focus on few of them, but the observation that I will make for the specific point is valid for the other operating parameters. And the background pressure, so it was kept under 10 to the -5 millibar xenon. Concerning now the experimental setup, so the campaign, the measurement campaign was realized in the P12G test bench, which is a really big, let's say, vacuum chamber, in which actually you have a rotating arm on which are positioned so the different diagnostic, so the RPA, the Faraday cup, and the Langmuir probe. Concerning the cluster configuration, so we have tested 2 different configurations. Basically, the configuration 1, which is, let's say, the FAR configuration, which a distance of 11 centimeters between the 2 thruster center line, and the configuration 2, which is the close configuration with a distance of 6 centimeters between the 2 thruster center line. You have to keep in mind here that when we rotate the arm in positive angle, we are at the position of the thruster head 1, and in negative angle, we are at the position of the thruster head 2. Also, an important observation here is that the Faraday cup at the 0° position is aligned with the cluster center line and not with one thruster center line. Which is important to remember because we have to take that into account when we do the post-processing. So let's start here with the ion current density angular profiles that were obtained with the Faraday cup measurements. In blue color, so you have the angular profile that were obtained for thruster head 1 and thruster head 2 working independently. I mean by that they are not in a cluster configuration, but we fire one, then we fire the other one independently. In red, you have the cluster. So basically the 2 thruster head working together simultaneously. And in yellow, you have the thruster head 1 plus the thruster head 2, which is basically the sum of the 2 angular profile obtained for these 2 thruster heads. You also have here the ratio between the ion current density of a cluster head the cluster, and the sum of the 2 thruster heads. So what we can make here as some remarks is that firstly the shape is conserved. I mean by that when you compare the sum of the 2 thruster head and the cluster angular profile, the shape is conserved, is the same. So you have the wings at the -60° position. But now concerning the ion current density, we see that we tend to underestimate the ion current density in the core of the plume when you do the sum of the 2 thruster head, and we tend to overestimate it in the wings at large angles. From this plot, so we can compute actually the total ion current So basically, this is the formula that we obtain, that we apply when you have a single Hall thruster operation, which is centered with the Faraday cup at the 0 degree position. But here, as I was saying, we are not aligned with it at the 0 degree position. So we have to take that into account. And we apply the formula that I will call the Formula 1 by taking into account the fact that the distance between the anode and the Faraday cup varies with the angle. So we do that by doing some trigonometric tricks. So this concerns the computation of a single Hall thruster operation when it is not centered. To compute now the total ion current for a cluster operation, we cannot really apply the previous formula that I was presenting. We have to adapt actually, because when you have a cluster operation, when you collect the current in the Faraday cup, you really don't know from which source comes from the plasma, because you have two thrusters that are operating at the same time. The only way to take that into account is to apply a correction factor, which take into account the fact that the distance between the Faraday cup vary between the Faraday cup and each anode block vary with the angular position. So I will call this formula the Formula 2. So now let's see the total ion current. So you have the thruster head 1 and the thruster head 2 with the different operating parameters, the discharge current for cluster and single operation. What we can make here as an observation is that the discharge current increase in cluster operation compared to the single operation, which can be explained by the fact that you increase in the vicinity of the thruster the pressure, so you tend to increase also the discharge current. Same observation here for the thruster head 2. Now, by applying the Formula 2 to the angular profiles that I was presenting, we can compute then the total ion current for the cluster. So here we have 0.74. And also by applying the Formula 1, we can compute the total ion current for thruster head 1 and thruster head 2. And we can sum these two values and we obtain 0.82, and we can compare now the total ion current between the cluster and the sum of the two, and we can see that we tend to overestimate actually the performances when we sum the two thruster heads. So it means that for now, so it has necessarily an impact on the beam efficiency and the mass utilization efficiency that are directly linked to the total ion current. So it means that we tend to overestimate performances, and we need to adapt the model to take this overestimation into account. We can also compare the total ion currents between the two cluster configurations. So as a reminder, the first configuration is the far configuration, and the second configuration is the close configuration. And we can see that the performances are better for the configuration 1 compared to the configuration 2. This can be explained actually by the fact that when you are in close configuration, and as we have large high magnetic field in low power Hall thruster, the two let's say the two topology influence each other, and so you influence the ionization processes and acceleration processes inside for each thruster, which impact necessarily then the performances. Let's continue now with the RPA measurements and the ion energy distribution functions that can be determined thanks to the IV characteristic obtained with alternating potential analyzer measurements. On the left side, so you have the thruster head 1 operating at 300 volts, so in the single mode operation. And on the right side, you have the cluster operation for the same conditions. So concerning the left side, if you compare the two sides, actually, you can see that we have the same shape. I mean by that you have a maximum peak, of which the energy is close of the discharge voltage. But the main discrepancy actually concerns the width, the broadening of the signal, which can be determined by the full width at the half maximum. And you can see that this value tends to increase for cluster operation as you favor the production, you favor the elastic collisions and the creation of flow energy ions. From ion energy distribution functions also, one can determine also what we call the maximum energy, which is basically the energy relative to the maximum peak, and the mean energy, which is the integration under the curve of the ion energy distribution function. So we can compare the cluster operation and the single thruster operation. So concerning the maximum energy, we can see that we have the same distributions. So it means that when you operate a cluster, you do not influence on the maximum energy. But on the other side, you have the mean energy. And here you can see that the two distributions are quite different. So you have lower mean energy for the cluster operation. And as I was saying before, we think that this is due actually to the fact that you favor the production of slow-moving ions as you increase the background, the pressure in the vicinity of the two thrusters. Now, here are other ion energy distribution functions, but this time for the cluster operated with two different discharge voltages. So the thruster head 1, which is at positive angle, was operated at 200 volts, and the thruster head 2 at negative angle was operated at 300 volts. So at the 0 degree positions, what we can see is that so we clearly see the two ion populations, so the 200 volt and 300 volt ones, and you have a higher quantity of 300 volts because, as we know, in the old thruster, when you increase the voltage, you tend to increase the ionization efficiency, and so you have in larger quantity you produce in larger quantity ions. Now, if you move to a positive angle, so at 20 degrees towards the thruster which is operated at 200 volts, we see that we favor the collection of the 200 volt population, which is quite logic because let's say the 300 volt plume, if I can say, is a bit hidden by the 200 volt plume, so you favor the collection of 200 volts. And same here at minus 20 degrees, so you have the 300 volt population which is present, and the 200 volt population tends to disappear.
Just one more minute.
Yeah, so conclusions. So we had some interesting results. So we were able actually to compare single thruster operation and cluster operation. But we see that the model is not reliable enough actually for the moment to determine directly performances and plume properties directly from a single thruster. So we need to develop a bit the model. And also in the future, so A-cross-B probe measurements were already made, but we would like also to make some LIS spectroscopy so that we can better understand actually the interaction between the two plumes. So thank you for your attention, and if you have some questions, I'd be glad to answer it.
Thanks a lot, Thibaut, for this very comprehensive paper about the investigation of the plume of low power Hall cluster. So we already have questions from the audience. Let me check. One hole from the guys in South Korea wants to ask you something. I think you can talk now. I open your microphone, one hole.
Yeah, I have read the question actually.
Okay. Yes, my question is, how do the magnetic field lines look like in the presence of two thrusters? And how do you compare it with plume angle?
That's a tough question. Actually, some mapping was made, but only for the configuration 2, so the closed configuration. Magnetic mapping was made between for the two thruster. And what you can see is that when they are close to each other, is that how can I say, the line inside, let's say, yes, inside the thruster, when they are as close as each other, they are changed by the position of the other thruster head. So it means that when you are at the inner position of the cluster, you influence directly the acceleration processes and you create a bit more divergence, but this is not the case for the outer position of the cluster. I don't know if it was clear.
Okay. So probably in the future, you're going to do the, how these interaction of the plasma will influence to the wall, like a wall erosion effect and so on.
Yeah, for sure. For now, actually, we do not really know because that's just, let's say, experimental step for now. But yeah, for sure, we do not really know how it impacts for the moment the erosion, and we need to make some lifetime test measurements to see if it has on the long term a real impact on it. But also, when you vary also the discharge voltage in each thruster. So if you put a 200 volt in one and 300 volt in one also, so you will also influence the erosion processes. So yes, for sure, that there is still some work to make from this side.
Okay, thank you for the nice talk again.
So we have time for the question from Christophe.
Yes, thank you for your presentation. I suppose that in your experiment, you have the two anodes with the same magnetic momentum.
No,
magnetic field in the same direction.
No, they were inverted actually. You were north pole from one side and south pole from the other side.
Okay.
To take yes into account the torque of the ions.
The swirl. Okay. Thank you.
Yeah.
Okay. Anyway, we have no more time for questions. So Thibaut, I want to thank you again for this interesting talk on cluster and plume interaction. And now we're gonna move to the
thank you
of this morning session. So the last speaker is Victor Desangles from Onera.
Okay, good morning, everyone.
Good morning, Victor. So Thibaut, you have to leave.
Yeah.
Perfect. So Victor,
okay.
The floor. Try to
my screen.
Yes.
Do you see?
Yeah, it's perfect.
Okay, I will just
enlarge it.
Full screen. Okay.
Yes, it's perfect. So you've got 15 minutes, Victor.
Okay, thank you very much. So good morning, everyone. So I'm Victor Desangles. I'm working at Onera. I will present you today the work that we have done during the Minotaur project. So the H20 Minotaur project. So the H20 consortium was composed of 7 partners that are listed here, but I will focus my presentation today on the study that we did at Onera with Justus Liebig University in Germany. In fact, because this is the work that has been done on the prototype and the work that has been involved in the most. So here is a quick reminder of the working principle of an ECR thruster. So an ECR thruster is composed of a plasma source here that is basically the extension of the coaxial microwave line that is feeding the microwave power to the thruster. So the source is composed of an inner conductor and an outer conductor. There is also the backplate that is making the transition from the coaxial line to the source, and the gas is injected to the thruster through this backplate. There is as well an annular magnet that is at the back of the source and that is generating the magnetic field that allows both to have the ECR condition met close to the backplate, and so to allow for a good transfer of energy from the microwave power to the plasma. And also this magnetic field is used as a magnetic nozzle to improve the performances of the thruster. So the main advantages of this technology is that it's a very simple design with no cathode and no igniter. So this will imply simplification of the PPU. But also we are demonstrating that this technology can produce very good performances. So the measurements that I will present today have been acquired either in the B61 vacuum chamber at Onera, that is a chamber with 9,000 liters per second pumping speed for xenon, and a simple single pendulum thrust balance, or in the jumbo vacuum chamber at the GLU. It is a bigger pumping speed vacuum chamber with a different balance. It's an inverted double pendulum balance, but both these balance are absolutely calibrated, so this allows us to compare the results. So here is the results of the first campaign that we did with the first prototype of the ECR thruster in 2018 at the beginning of the project. And so we've been very surprised to see that we saw a big difference in performances. Here you see on the left plot the thrust that we've measured against the vacuum pressure. And so in fact, when you decrease the vacuum pressure, when you have a better vacuum, you increase quite a lot the performances of the ECR thruster. And we have made the experiment to add gas in the background artificially to increase the pressure, and we see the thrust decreasing with this pressure. There is still a surprising phenomenon is that we have an offset between the two curves, the one measured at Onera and the one measured at GLU. The current hypothesis for this is that the chamber size has an effect on the thruster, but we are not sure yet. Why the performances are increasing with the pressure? So we've measured that all the different figures that will allow to compute the thrust, so the ion current density, angular distribution, as well as the ion energy is increasing actually when we are decreasing the pressure. So having a very good background pressure is very necessary to measure the good performances with those ECR thrusters. The first job that we did during the H2020 project was to improve, to optimize the thruster geometry and design. So that what we did is we did quite repetitive measurements, changing the length and the diameter of both the outer conductor and the inner conductor. What we have ended up selecting is outer conductor that is 20 millimeter long, inner conductor that is also 20 meter long, and the diameter of the inner conductor that is 2.3 millimeters. The outer conductor has a diameter that is 27 millimeter. I would like to outline here the measurements that are presented on the right side of the slide, where you see that the specific impulse produced by the thruster increase when we increase the inner conductor diameter from 1.2 to 2.3 millimeter, but then it stays stable when we keep increasing the diameter of the inner conductor. This is very important because this will allow us in the future to increase the diameter of this inner conductor to increase the lifetime of the thrusters, as I will present later. There is a certain type of optimization that we did is an optimization on the material of both the conductors and on the coating. So I will not focus my presentation on this today, but you need to keep in mind that these material and coating are also very important to access very good performances. So after this optimization, we went back to GLU to make a second performance test. So we varied the mass flow rate and the power that we are giving to the thruster and measuring the thrust and the ion energy. We were able to make nice maps of thrust, specific impulse, thrust to power ratio, and thruster efficiency against those two control parameters. We have extracted from this map some points of interest that are summarized here in the table on the bottom. So what I would like to highlight here, is the improvement in the performances that have been done during those 2 years of test and optimization of the thruster. So the thrust have been quite multiplied by 2, and it's the same for the ISP and the thrust to power ratio, which lead to a thruster efficiency that is improved quite a lot from 30% to 44%. Changing the mass flow rate and the power, you can actually make some compromise to choose to have a higher thrust, higher ISP or higher thrust to power ratio, and choose in which working regime you want the thruster to operate. Based on this conclusion, we've decided as it was a goal at the beginning of the project to develop a bigger thruster. So we aim at 200 watts. So what we have decided is to keep the power to the area in the backplate constant, to go from the 30 watt to the 200 watt version. So the 200 watt version has now a diameter that is 70 millimeters, so it's a bigger thruster. And we add then to design a new permanent magnet that fit this new dimension. We then test this 200 watt thruster in jumbo vacuum chamber. And interestingly, we have obtained quite similar figures than for the 30 watt thruster. I mean that we have similar ISP, about 2,800 seconds, similar thrust to power ratio, we can go over 60, and over total, and kind of the same total thrust efficiency, about 50% at the maximum. The thrust is in fact higher. We can go up to 7 millinewton. And here I have chosen to show you an intermediate point that is kind of compromise between all these figures. And what is interesting to see is that these compromise actually occur at 150 watts as we were targeting 200 watts. So there is a scaling law that we do not capture for the moment for the thrusters, but that will be interesting to investigate in the future. The last test that we did at GLU was kind of a short endurance test, I'll call it. So we looked at the performance stability for the 200 watt thruster for 100 hours of quite continuous operation. So what you see on the top plot is that the thruster operates at a constant thrust for these 100 hours. I would like to highlight the fact that we stopped the test because the vacuum chamber was not available anymore after those 100 hours. But the thruster was still operating very fine, so we could have kept going with this test a much longer time. We also check what is the erosion of the inner conductor, because it's the part of the thruster that erodes the most, and you can see it by eye when you run the thruster for a long time. So what we've noticed is that, first of all, the loss of mass of this inner conductor is linear with time. We measure the rate of 0.2 milligram per hour for the 30 watt thruster and 0.06 milligram per hour for the 200 watt thruster, so 3 times less. This leads us to compute an estimated lifetime that is based on the disappearance of half of the mass of the inner conductor. And this gives us about 500 hours for the 30 watt thruster and 1,700 hours, for the 200 watt thruster. We are quite happy with those figures for the moment. We think it's already a good achievement. And also we are quite confident that we can increase those numbers quite easily by increasing the diameter of the inner conductor without losing any performance, as I told you before. I will go quite quickly on the next 2 slides. So first, we have tried to assess if the thruster was emitting a lot of microwave. So what we see is only 0.1% of the radiated power seems to be emitted in the vacuum chamber. So this is not a proper CEM measurement, but it's already some interesting facts. And also we have made a proof of concept of magnetically driven thrust vectoring. And we achieved for the first prototype that we've made plus and minus 3 degrees for 15 watts of consumption for this prototype. I will now conclude this presentation. So first of all, we were very happy with the new performances of the thrusters, with development of the 2 prototypes, and by the fact that we have demonstrated that the thruster can work steadily for 100 hours. I would also want to say a word about what has been done by the other partners, because they did a really good job. TMI developed a microwave generator that is adapted to the 30 watt thruster. So it can develop 22 watts with an efficiency of 72%. And it's a very small microwave generator. It's about 0.2 liter for a couple 100 grams. Safran and Thales Belgium also look at the impact of the ECR technology on mission costs. One of their findings is that the simplification that is bring by the ECR thruster compared to old technology to the PPU, let us think that the PPU may have its cost reduced by something like 50%, so it's quite a lot. And the last thing I want to say about this is the development of numerical simulation tools by our colleagues in UT3M. So they have developed an hybrid code that is very much adapted to the simulation of our ECF raster. And they already published those results. And we are now working on a very detailed comparison between experimental and numerical detail, hoping for publication in a short time. You can find more detail about what have been done by the other partner of the Hatch 2020 on this presentation on the EPIC website. I'm putting the link here. For the perspective, in the short term, we would like to try to pair the power supply developed by TMI and our thruster to test it together in a vacuum chamber. And we also want to look at alternative gases because krypton seems to be very promising since the numerical simulation led at UC3M. I would like to conclude my presentation by showing you what we are currently occupied at. So we are developing a new vacuum chamber at Onera. So it's a way bigger vacuum chamber. It's 5 meters long, and it has an auxiliary vacuum chamber that is 1.25 meter in diameter with a full opening gate valve to be able to change the thruster geometry very quickly. What is specific with this vacuum chamber, it has cryopanels that is specifically designed for electric propulsion, and the cryofluid circulation is in closed loop. So we are hoping that we can make some savings on the cryofluids for example, for long test, endurance test. We are targeting 100 liters per second pumping for xenon, and the pumping speed will be starting next week. So we are really onto this. So thank you very much for your attention, and we'll be very happy to take any questions if there are some.
Thanks a lot, Victor. It was really great to have an overview of this Minotaur H 2020 project. And I must admit that the numbers are super impressive. I mean, thrust efficiency at such a low power, that's really very interesting and certainly promising technology. There are questions from the audience. I just want to ask one myself, and since I'm a chairman, I can do it. You're not, are you thinking about delivering a product at the end? Or?
Yeah, of course. That is not what we are used to do at Onera. We are more working on doing science and development research. So we are coming onto it, of course. And so we will see what we can do in the next future about this. So we want to focus on validating what we can do on the pairing of generator on this thruster, because this is not something that is usually done at this frequency. And then I think we can have a better view of is this product can be industrialized very soon, or do we need to have a lot more work to do? So yeah, we are going into this.
Okay, thank you. So now we have a question from Yevgeny Raitses from PPPL.
So sorry, I don't see the question right now.
Well, I can.
Yeah,
can you
okay.
hear me?
Yeah.
Hello. Very good, very impressive. I agree with Stefan. It's a very impressive result. I have actually two questions. So first, more specific, can you show a schematic of the thruster and show precisely where the inner conductor is?
Yeah, of course.
First.
Sorry, maybe,
second, right away, can you explain me physical what's the physical mechanism behind such super performance?
Okay, of course. So maybe this is the best schematic drawing. So the inner conductor is here in black. So it's directly connected to the inner conductor or the coaxial line, okay? That brings the microwave power. And then the outer conductor is this part here. It's the outer conductor, it's the outer part of the source. And it's also electrically linked to the outer conductor of the coaxial line, okay? So the mechanism, the physical mechanism, so it's based on the deposition of power by electron cyclotron resonance. So you see here in color outline the magnetic field that is around 875 Gauss, okay? So it's at this magnetic field that happens the ECR for 2.45 gigahertz excitation. And so in this location, we will give a lot of energy perpendicular to the magnetic field line to the electrons. And then in the magnetic nozzle, this perpendicular energy given to the electrons will transfer to parallel velocity of the electrons. So the electrons will be ejected of the thruster with very high velocities. And this will generate an ambipolar electric field that will accelerate the ions, which will produce the thrust.
Yeah, I understand it, but but it's a very high efficient regime. So it's basically a thermal machine. So you're heating up electrons, and when you accelerate electrons, from electrons you accelerate ions. So even steam machine is not so effective. So basically you accelerate it in both directions, right? So you're also pushing it back to the inner conductor. So my question is, was it like estimated or physics model backup with kind of high performance just based on mechanism you described?
Yes, so this is what we believe, of course.
No, like a physical model kind of calculations.
Sorry,
or something.
Can you repeat?
Like, do you have like a physical model calculation which such acceleration can actually allow you to achieve 50% efficiency?
Do we have a modeling of this? This is your question.
Something like that. Right?
Can you retrieve those numbers by modeling?
Yeah. We don't have those numbers by modeling at the time. No.
Thank you.
Efficiency is a bit lower. Yeah.
Okay, so is it fine, Evgeny?
Yeah. Thank you very much.
Okay, so we have a last question from Marco Inchongoro from UC3M. Marco.
Hello. I just wanted to ask you, what was the main aspect that allowed you to reach such a nice efficiency? Because I remember that from your last papers, you were below 20%. So yeah. This means more than double. How did you achieve this?
Yeah. So interestingly, not one aspect. So each aspect that we've changed, the geometry, then material for the inner conductor, then material for the outer conductor, all of these aspects adds up quite evenly, and we have measured separately those different aspects. So we can track the increase in efficiency given by each of those improvements separately, and they are contributing quite the same amount. Yeah.
Okay, thank you. And I understand that in order to commercialize this product, you would have to take into account also the efficiency of the microwave power supply.
Of course.
At which point in the development you are about this?
So yeah, I want like to precise that the figures that I show are only taking into account the power that is deposited to the thruster and not the power that would be given to a power supply. So that will reduce the efficiency. We want to, as I said, try the power supply that has been developed by TMI, which would be pretty much ready for a 30-watt thruster. For higher power, it's a bit more complicated because having a very effective power supply for a 200-watt thruster is not something that's ready. So we are working on it. We have different leads that we want to follow. The first one would be to pair together different power supply like the one developed by TMI. Another aspect would be to try to develop a new source of our power, higher power, that is that would be dedicated to higher power. Yeah, but this is not done for the moment.
Okay, thank you a lot.
Okay, thanks a lot, Victor, again for this very interesting.
Thank you very much.
Thruster. So now it's time to give the floor to the last speaker of the morning session. So Marco Inchogoro from UC3M. And this will be another paper about ECF thruster. So Marco.
Yeah, 1 second. I have a problem with the video.
Okay. we have time because it's the break afterwards.
Okay, I have it. Okay, I can start sharing.
Yes, yes, you can.
Can you see?
Yes, just have to enlarge it and it's fine. So you've got 15 minutes, Marco, and we have 5 minutes of question afterwards.
Okay, so thank you for the introduction. So today I'm going to talk about the first efforts in the first experimental campaign on the newly designed circular waveguide of the EP2 group. This short presentation will be organized as follows. We will have a short introduction, a description of the ECR thruster and the experimental setup, the results, and the conclusions. So starting with the introduction, so this work is part of the Prometeo project, which is a mutual collaboration between the CEMAT National Fusion Laboratory and the EP2 group. So in this context, we developed a waveguide ECR thruster prototype because it has been shown during the H2020 Minotaur project to be a promising candidate for in-space propulsion, like we saw in the last presentation. So an electron cyclotron thruster relies on two basic physical mechanisms. So we have the electron cyclotron resonance for ionization and plasma heating, and the magnetic nozzle for plasma acceleration. Both of these mechanisms require a magnetic field for them to work. And in particular, in the case of the electron cyclotron resonance, the magnetic field determines the resonance position. Instead, for the magnetic nozzle, it determines the nozzle shape. So microwaves are injected from the back of the thruster through a quartz window, and then the neutral propellant is injected into the thruster chamber. So the free electrons are directly heated by the microwaves, and thus they ionize by collisions the neutrals. Then the plasma is going to be accelerated by the amipolar field in the magnetic nozzle. Okay, so this thruster can be designed into different ways, we have the waveguide design and the coaxial design that we just saw in the last presentation. But for this work, we decided to go for a waveguide ECR thruster because, first of all, we wanted to understand if we can achieve such good performances also with this design, but also we wanted to reduce the problematics and the losses associated with the central antenna that here is not present. Okay. So our team is tackling this problem from both the simulation and experimental point of view, but for this conference, we are going to talk about only the experimental part. In fact, these are the latest results that we obtained, and indeed we were able to achieve the first ignition and perform some preliminary characterization of this prototype. Okay, so now I can describe a bit the thruster. One of the main disadvantages that you get when you switch to the waveguide configuration is that now the thruster dimensions are limited to, are dependent on the microwave frequency. For this reason, we decided to use a 5.8 gigahertz source in order to limit the dimensions and the power requirement. Furthermore, the design has been the thruster has been designed as a breadboard in order to be able to change actively all the components in the design, and also this is eased by the fact that the magnetic field generator is completely separated from the thruster. The magnetic field generator is composed by two elements. We have a radially magnetized ring magnet made of samarium cobalt, and the coil which so the magnet creates the field necessary for the resonance and also determines the shape of the magnetic nozzle. But we can use the coil to affect this magnetic field topology. In particular, we can see here what happens when we change the current. We can see that going from 0 ampere to 40 amperes, we are displacing the resonance position, which is placed here in blue, towards the exit plane, and also we are reducing the divergence of the plume. In order to deliver the microwave power to the thruster, we need a transmission line, and the typical transmission line for this frequency is in the waveguide format. This is what is represented here. Each of the components are waveguides, and here we can see the microwave generator, which is a magnetron, included an isolator to isolate it from the reflected waves. And here we can see a bidirectional coupler, which allows us to measure the forward and reflected power in order to estimate the power delivered to the thruster. Furthermore, here we have a stub tunnel, which is a matching network useful to match the transmission line to the plasma impedance. And finally, we have the interface between a vacuum and air, which is realized by a pressure window attached to a custom vacuum chamber flange. Inside the chamber, we have flexible waveguides to ease the alignment of the thruster, and a DC waveguide vacuum gap, a DC block, to ensure that the thruster is floating during all the operations. So now I will describe the experimental setup. Here we can see how the setup looks like with a section of the vacuum chamber. So this is the air side with a waveguide transmission line. This is the flexible waveguide I mentioned before, and this is the thruster stand. Okay, so on the plume side, we have mounted a polar probe positioning system in order to be able to scan the plume with probes. The probes used in this case were a Langmuir probe and a Faraday cup. The Langmuir probe was moved in the axial direction to the thruster, and the Faraday cup at a constant distance of 40 centimeters from the exit plane in the theta direction. Furthermore, during this campaign, we tracked also other parameters, like, for example, the floating potential and the temperature of the thruster walls. Two different designs configurations were tested. We have the single injector and double injector configurations. The thruster is always the same in the two cases, and it presents always two injector holes inside the thruster chamber. But in the single injector case, only one hole is used and the other is capped, it's closed. Whereas in the double injector configuration, both of the holes are used at the same time. We did this in order to study what is the effect of the injector on the symmetry of the plume. Okay, so now going to the results. So the first thruster ignition was obtained for the single injector configurations. The ignition is very easy to obtain. It's just necessary to establish a constant mass flow rate and a constant power in whatever this working point is inside these ranges, and the thruster will ignite very easily. We can see here how the plume looks like when the thruster is working at 175 watt and 8 ccm of xenon, and we already see some asymmetries. But we will talk about this later. What I want to show here is that the reflections that we experienced, the microwave reflection that we experienced during this campaign, were quite high. In particular, for the single injector configuration, we can see that they reach up to 37%, and this creates problems in the measurement of the power delivered to the thruster, because increase the error. But in any case, we see that going to high mass flow rates, generally it increases it reduces the reflection, and this minimum of reflection displaces towards lower mass flow rates when the power is increased, and we can see it here. So the asymmetries visually seen in this picture were also confirmed by the Faraday cup measurements. In particular, here we can notice the azimuthal scan of the plume with the Faraday cup when the mass flow rate is constant and the power is changing. First of all, we notice that two peaks are present, so the plume, we can say it's hollow. And also we notice that that the utilization efficiency is quite low, and of course it increases with the power as expected because of higher ionization. Furthermore, this is what happens when instead the mass flow rate is increased with a fixed power. So again, there are a lot of asymmetries in the plume, but we notice a pattern. So we start with a single peak for low mass flow rates, but when we start to increase mass flow rates, two peaks start again to appear, probably for the interaction with the walls. Okay, so also some Langmuir probe measurements were performed as mentioned, and we were able to reach a temperature of 25 electron volt, which is quite in line what we can find in the literature for ECR thruster, but usually for a lower power. Here we were working at 300 watt. So for the double injector case, here instead we can see all the working points that we tested and we measured. here we are increasing the mass flow rate, and here we are increasing the power. So we notice two things that happen when we increase the mass flow rate. First of all, the plume becomes more and more red. You can see it very clearly. And also, as before, the plume looks like it's opening, becoming presenting wings towards the lateral walls. Furthermore, we can see clearly that the symmetry in this case is much more improved with respect to the single injector case. So considering the center line, now we can show the Faraday cup measurements. So again, the symmetry is almost perfect. And we notice again how at low mass flow rates, we have a single peak, but when we started to increase the mass flow rate, other peaks start to appear. So we also tried to vary the coil current while with a fixed working point, 175 watt and 2 SCCM of xenon, and we switched the coil current from 50 to minus 40 ampere. You can see what happens to the plume here. So it's clear that a higher current, as explained before in the previous slide, will make the magnetic nozzle less divergent, and reducing the current or putting a negative value will increase a lot the divergence. And we can see this behavior also in the Faraday cup measurements. So all the Faraday cup measurements allowed us to measure the utilization efficiency, and is still quite low also for the double injector case. We reached a maximum of 70%, but this is decreasing very fast as the mass flow rate increases or the power is reduced. Furthermore, as mentioned, I measured also the floating potential of the thruster, which allows to have first a preliminary underestimation of the ion energy, and we can see that is scaling with the inverse of the mass flow rate, as you would expect from this parameter. Furthermore, here I show the plasma potential obtained with the Langmuir probe, varying the distance from the exit plane. And we notice how even after 40 centimeters away from the exit plane, the ions are still going to be accelerated by the ambipolar field. Okay, temperature were measured along the overall campaign, temperature measured on the thruster walls. We can see here what happens for a normal scenario of measurement. We see that there are different peaks. These peaks are different working points being tested, but what we notice is that for each of these working points, we have a different slope in the temperature. So the temperature increases faster or slower depending on the working point. This is a clear indication that the power going to the walls is changing depending on the working points. It happens that the power to the walls is scaling with the slope of the temperature when the thruster is firing and when it is cooling, minus when it is cooling. So knowing the rate of temperature when the thruster is cooling, which can be measured, we can obtain an indication of what is the power, the trend of power going to the walls. This is what is plotted here. It's just a trend, so these are not actual values in percentage, but it is normalized with the power delivered. So we can notice for very clearly that going to low mass flow rates, the power going to the walls is greatly reduced with respect to high mass flow rates. So this is a very easy technique and can be done essentially in every experimental campaign, because the thruster temperature is something that is normally always tracked. So if we do a preliminary estimation of the actual power that is going to the walls, we can assess about from 10 to 60% in the of power going to the walls of the coupled power. So it's quite a lot. Furthermore, some interesting aspects were also found when watching the thruster from the front view. So in this case, we are at constant power and we are varying the mass flow rate. So we notice that, first of all, there are always two bright spots that are the injector points, but something peculiar is that for high mass flow rates, the plasma appears to be rotating counterclockwise, whereas for low mass flow rate, it appears to be rotating clockwise. So there are a lot of patterns here, and we are not sure what they mean and what is the source of this, but some speculation could be that these are related with with the peaks that are developed different mass flow rates in the plume. So other analyses are going to be needed in order to study this phenomena better. We plan to use a fast camera and also some different injector types to see what happens. Finally, the conclusions. So we can consider this experimental campaign very successful because we managed to ignite the thruster without any problem, and also we were able to perform some preliminary plume measurements and discover some interesting characteristics. First of all, we saw that the utilization efficiency is quite low, and it reduces considerably the thruster performances. Furthermore, we noticed that the thruster is probably working better at low mass flow rates. And also we noticed that the reflections are quite high for basically every working point. So this is something that really needs to be improved. So for the next campaign, for sure, we are going to improve these aspects. We are going to use a VNA to improve the matching for the transmission line. And also we're going to test other thruster configurations with a radial diffuse injector and testing different chamber lengths, hoping to increase the utilization efficiency. Furthermore, we are going to use other diagnostics like a thrust balance and RPA. So thank you. If you have any questions or comments, please don't hesitate.
Thanks a lot, Marco, for this very interesting talk about the development of your ECA thruster in Spain with a different approach compared to one that has been described previously by Victor from Onera. So we already have we have many questions. So I have already a question from Burak.
Hi, Stefan. Can you hear me?
Yeah.
Okay, thank you for the presentation. I'll just be quick. I think the most interesting observation to myself is that with changing the current direction, the plume becomes more diffuse. Do you have a reason, explanation for that?
Yeah, of course. 1 second. I cannot go back. I don't know why. Okay, now yes. You can see it. No, oh, sorry. Okay, so in this plot, you can see what happens when the coil current is changed from 0 to 40 amperes. And you can see that the divergence is reduced. So going to a lower current, so a negative current, will change the direction. So will increase the divergence instead of reducing it.
Yeah, but the current level is the same, 10 amp minus 10 amp. And I think ECR region should be in the same region or location, right?
Sorry, what do you mean?
I mean, let's say for 10 amp and minus 10 amp, the strength of the magnetic field is the same, and the ECR location, like
no, the strength of the magnetic field will not be the same because you're putting current in a coil, so it will create a magnetic field.
Yes, but for the same current, you're applying the same current, same number of wire turns.
No. Okay, so it's because we also have a magnet creating, so there will be an interaction between the two fields, and the actual geometry of the topology of the magnetic field will change if you use the coil.
Okay, I missed that part. So you also have permanent magnet there. Okay.
Yeah. The permanent magnet creates the base field, and then we use the coil just to affect the topology of the field.
Okay, thank you. Thank you.
Thank you, Burak, for your questions. So now we have a question from Francesco.
Yes, could you hear me?
Yes, we can.
Okay. Ciao, Marco. Could you go to slide 19, where you show the variation of the reflected power?
Yes.
Do you have an idea why such important variation? Since I mean, you are using a matching network, right? So
no,
the matching network should avoid this variation. That I mean, is it change in order to make the absorbed power the maximum as possible for the different plasma impedance, right?
Yes, you are perfectly right, but oppositely to check how the reflections vary with the mass flow rate and power, we were not using the matching network in this campaign. We tried to use it in a couple of tests, but yes, we managed to match. but for some other cases, the thruster was behaving not nominally, and the thruster could not be kept ignited for some period. So there are still some tests that have to be done in order to use efficiently this matching network.
Okay.
We didn't use it in this case.
Okay. Thank you.
Okay, thank you, Francesco. Victor, do you want to add something? The hand up.
Yes, okay. Thank you, Marco, for this presentation. I had the same question than Francesco about how to use the matching network and if you can succeed to have the matching. I also wanted to ask you, it's a very nice system that you've designed to change the divergence of the magnetic field. So it's very nice. And I wonder if you have an idea of how this will impact the performance. I understand that as the magnetic field is diverging more, the plume will be more diverging, but do you have an idea of how it would affect, for example, the ion energy and the performance?
Okay, so we didn't have any measurement of the ion energy, but I can give you some information. So first of all, when we are changing the current in the coil, we are not only affecting the magnetic field topology, but also the resonance position. So this is something that needs to be taken into account. We can actually test some configurations with a very similar magnetic ACR resonance position by displacing the distance between the magnet and the coil, but we didn't do it in this campaign, and it could be done in future. And in this way, we can just alter the magnetic field topology and not the resonance position. But concerning to your questions, I prepare like an additional slide to what happens when for the ion energy. Okay, so here you can see the floating potential when we vary the current. So the floating potential of the thruster can vary a lot with when the coil is being used, and it is actually very dramatical. And you can see that it can go to very low values, even negative values, to increase linearly. So it depends really on the working point that we use for the coil. So the ion energy can vary greatly depending on the actual coil current that we use.
Okay, thank you very much.
Okay, are there any other question in the audience? I just have a question, quick one. Before we go for lunch, about the window for transmission of the wave.
You mean the interface between the chamber and the? Okay.
In here, but you will anyway have to inject into your cavity, right? So you will probably use a window even with the next version to separate the ECR cavity and the waveguide. No, you always have a dielectric somewhere.
So you don't mean the interface for the chamber?
No,
you mean
no, I mean
okay. One second, I go again to this slide. Yes, as you can see it here.
Yes, exactly. Of course, there is probably a minimum thickness due probably to the pressure. I don't know. And I can imagine that the thinner, the better it is. And what about the material that you?
Okay, for this window, we use the quartz, because it's the best material to be used for microwaves. It has the lowest absorption that you can find. Yes. So yes, this is what we used. And at the moment, we didn't try to use other thicknesses. And
to switch off your microphone. No, but I can do it.
We didn't try other thicknesses, but we wanted to be safe because it can be subject to high heat fluxes, so we didn't want it to break. So for the moment, we kept, if I remember correctly, it's 4 millimeter, but we might change it in future. So this is the first iteration. We necessarily will alter some dimensions and other parameters in the next designs.
And the cavity is fully metallic, right?
So this here. So all these components in dark gray are in stainless steel, and this is in aluminum. This is quartz, and we have an FFKM O-ring inside this little hole.
Okay. Okay. Thanks for this information, Marco. So there's no more question from the audience. So I would like to thank again all the speakers for the second part of the morning session, for the interesting talk on all thruster and ECR thruster. So now it's time for break, for the lunch break. So we will restart at 2 p.m. with an invited lecture from a Gamma Space. So enjoy your lunch, and we meet again in a bit more than 1 hour. Laurent, t'es là? Tu m'entends, Laurent? Est-ce que tu es là, Laurent? Je sais pas.